Hello there, and welcome to the Cosmographer. There is a planet on this list that is losing itself at up to 15 Earth masses every billion years, and in 400 million years there will be nothing left of it at all. Number 17 has a year 16 hours long, and an atmosphere in which iron glows hotter than the ground beneath it. Number 10 sits 7,000 astronomical units from its own star, on an orbit that takes 900,000 years, so a single year there is longer than the whole history of our species. Number 15 is where humanity first detected air on a world beyond this solar system in 2001, and then watched that air being stripped away. 20 worlds, counted down from 20 to 1, every one of them found, catalogued and measured, and every one of them permanently beyond reach. Get comfortable and settle in. If quietly working through 20 real worlds nobody will ever visit sounds like a good night to you, a quick like and subscribe helps this channel reach more curious minds like you. Because by the end of this list, the world at the top will not be the farthest away or the strangest. It will be the one nobody can prove is there. Let's begin at number 20. Number 20, the first rocky world anyone ever confirmed, and it has no ground. There are worlds in this galaxy that we have found, measured, weighed, and named, and that no human being will ever stand on. Not one of them is a secret. Every world on this list has a catalogue number, a discovery date, a published set of numbers, and a small library of papers written about it. What they have in common is not that they are hidden. It is that each one sits behind a barrier of a particular kind, and the barriers get stranger as we go down. Some of the barriers on this list are made of matter and energy. Those come first, and they are the easy ones to understand, because a world that would vaporize a visitor is a world you can picture. Later, the barriers stop being physical. They become barriers of distance, of time, of what the world is made of, and finally, at number 1, a barrier of a kind that nothing in our own solar system prepares you for. The last world on this list may not be unreachable because of how far away it sits. It may be unreachable because nobody can establish that it is there. None of these worlds are in our solar system. That is a deliberate choice. We have landed on Venus, driven across Mars, dropped a probe into Jupiter's clouds, and set a lander down on a moon of Saturn 1 billion kilometers from home. Every one of those places is difficult, and none of them is impossible. The nearest world on this list is 41 light-years away. The farthest is 7,500. Between those two numbers there is no rocket, no engine, no arrangement of chemistry and patience that would carry a person to any of them. They were found, they were measured, and they are permanently out of reach. So let us begin with the one that started the rocky half of this story. On the 3rd of February 2009, a French-led team announced a planet that changed the shape of the field. The telescope was co-rot, operated by the French Space Agency with participation from the European Space Agency, and the discovery paper carries the name of Alain Léger and his colleagues. The planet was called Co-Rot 7b, and what made it matter was not its size or its temperature or its orbit. It was that Co-Rot 7b was the first exoplanet ever shown to be rocky rather than gaseous. Before that announcement, essentially every planet found beyond the Sun was a giant. That was not because giants are more common. It was because giants are easier to see, and the instruments of the 1990s and early 2000s could not reliably detect anything smaller. So for more than a decade, the catalogue of known worlds was a catalogue of Jupiters, and the question of whether rocky planets like ours were common or rare stayed entirely open. Co-Rot 7b closed that question. It sits roughly 489 light-years away, based on the modern Gaia parallax, and older papers put it nearer 520. That difference is not a disagreement about the planet. It is a refinement of how far away its star is. Now, the orbit. The period is 0.853585 days. That is 20 hours and 29 minutes. A year on Corot 7b is shorter than a single day here. The semi-major axis is 0.0172 astronomical units, which works out to about 2.5 million kilometers from the star. To feel that number properly, put it beside Mercury. Mercury orbits the Sun at 58 million kilometers, and Mercury is close enough that its day side reaches 430 degrees Celsius. Corot 7b is more than 20 times closer to its star than Mercury is to ours. The radius has held up well over the years. It sits at 1.528 Earth radii, give or take about 0.065, which makes the planet roughly half again as wide as our own. The mass, on the other hand, has never settled, and the reason why is worth a moment, because it explains something about how this work actually gets done. To weigh a planet by radial velocity, you watch the star wobble as the planet pulls on it. The wobble is tiny, and the measurement is a spectral shift of a few meters per second. The problem is that stars are not smooth lamps. They have magnetic activity, spots that rotate in and out of view, and surfaces that boil. All of that produces spectral shifts too, and those shifts can be larger than the planet's signal. Corot 7 is a young star, a G8 or K0 dwarf at 5,250 Kelvin with about 2% photometric variability. That variability is not instrument noise. It is the star's own face changing. So the published masses have ranged widely, depending entirely on how each team chose to model the activity. Queloz and colleagues in 2009, Hatsis in 2010, and again in 2011, Boisse, Pont, and Ferraz-Mello, all in 2011, produced values spanning from 2.26 Earth masses at the low end to 8.0 at the high end. Hatsis in 2011 gave 7.4 plus or minus 1.2. Hayward and colleagues in 2014 revised it down to 4.7 plus or minus 0.9. That same paper did something else useful. It showed that a claimed third planet in the system on a 9-day signal was most likely not a planet at all, but the star's rotation showing through. That is a factor of 3 in mass on a planet we have known about for 17 years, and it is worth sitting with, because it sets the tone for the rest of this list. These are not vague objects. We know the radius to 4%. We know the period to 7 decimal places. And the mass, which is the single number you would most want, is still argued over. The temperature measurements are what put this world in its place on this list. Leger and colleagues published a set of them in 2011. The substellar point, meaning the spot on the surface directly beneath the star, sits at 2,474 Kelvin, plus or minus 71. The night side sits somewhere between 50 and 75 Kelvin. That is a single body carrying a temperature difference of nearly 2,400 Kelvin across its own diameter, permanently, because it is tidally locked and the same face always looks inward. At 2,500 Kelvin, silicate rock does not merely melt. Galaxies will continue to drift. The stars overhead may appear eternal, but the great web of galaxies is always in motion. And that is where the phrase, "this planet gave to the field," comes from. The Discovery team proposed a class name for objects like it, and the name stuck, the Lava Ocean Planet. The predicted structure is a permanent magma ocean on the day side, with an atmosphere above it made of vaporized rock. Not hydrogen. not helium. Mineral vapor, silicon, and sodium and iron in the gas phase, drifting away from the substellar point and condensing back out as it cools toward the terminator, falling as something a person on the ground would have to call rain, if there were a person, and if there were ground. The confirmation work was careful. Spitzer independently validated the transit at 4.5 microns, with a depth of 0.426 millimagnitudes, plus or minus 0.115. The 8-micron observation returned nothing significant, which is an honest result, and was reported as one. There is one detail about the sky there that is easy to skip past. At 2.5 million kilometers from a star roughly the size of the Sun, the star would span about 50 degrees of the sky. That is not a bright disk. That is roughly 100 times the width the Sun appears from here, filling more than a quarter of the visible dome, unmoving, in the same place forever, because the planet does not turn relative to it. So this is where the list begins. The first rocky world anyone ever confirmed beyond our Sun, 17 years ago, turned out to have no rock you could put a boot on. Nothing solid has been confirmed at its surface in all the time since. Found, measured, and permanently out of reach. The next world on this list has no atmosphere at all, and it is close enough that we can describe the color of its stone. Number 19, the bare rock 49 light-years away. In September of 2018, the Transiting Exoplanet Survey satellite picked up a dip in the light of a small red star, and Van der Spek and colleagues published the result the following year in the Astrophysical Journal Letters. The planet is called LHS 3844b. It orbits an M5 red dwarf about 15 parsecs from us, which is roughly 49 light-years. By the standards of this list, that is the house next door. The orbital period is 0.4629299709 days, which is a little under 11 hours. The radius is 1.286 Earth radii. And then the honest part, which belongs on air rather than buried in a table. No radial velocity mass has ever been confirmed for this planet. We know precisely how big it is, and almost nothing about what it weighs. That combination is more common in this field than most summaries admit. There is a practical reason this particular planet became the test case rather than one of the hundreds of others TESS found in the same period. The host star is unusually bright in the infrared. Its I magnitude is 11.9 and its K magnitude is 9.1, and those two numbers are why the whole story exists. A small planet produces a small signal, and a small signal is only measurable against a bright background. Astronomers did not choose this world because it was the most interesting one available. They chose it because it was the one they could actually measure, and then it turned out to be interesting for reasons nobody had specified in advance. The orbital period deserves a moment on its own. 11 hours is shorter than a working shift. A year on LHS 3844b begins and ends in less time than most people spend asleep and getting to work. The planet has completed more orbits since its discovery in 2018 than Earth has completed since the last ice age ended. And because it is tidally locked, none of that motion produces any change on the ground. The same hemisphere faces the star through every one of those laps, and has done for however long the planet has been there. The measurement that matters came from Spitzer, and it was published by Laura Kreidberg and colleagues in Nature in 2019. They took a phase curve at 4.5 microns, which means they watched the system continuously through a full orbit and tracked how the combined brightness of star and planet changed as the planet turned. That technique lets you separate the day side from the night side without ever resolving the planet as a disk. You are reading the shape of a curve, and the shape tells you where the heat is. The dayside brightness temperature came out at 1040 Kelvin, plus or minus 40. The nightside emission was consistent with 0. The phase offset was consistent with 0 as well. Those two zeros are the entire finding, and they are worth unpacking because they say something quite specific. On any planet with an atmosphere, heat moves. Air warms on the sunlit side, flows toward the cold side, and carries energy with it. On Earth, that circulation is why the tropics are not hotter and the poles are not colder than they are. On a tidally locked planet with a thick atmosphere, the effect is even more pronounced, and the hottest point in the light curve gets pushed downwind of the substellar point. That downwind shift is the phase offset, and it is one of the cleanest fingerprints of wind that we can measure from this distance. LHS 3844b has neither. No heat crosses to the night side. No hot spot is displaced. Nothing is blowing, because there is nothing to blow. The team put numbers on that conclusion. Atmospheres with surface pressures above 10 bar were ruled out at 3 sigma. Thinner atmospheres remain possible in principle, but a thin atmosphere around an active red dwarf is a temporary condition, not a stable one, because the stellar wind erodes it. The bond albedo came out below 0.2, which means a dark surface. The data fit a bare rock model well, and the best candidate compositions were basaltic or ultramafic. In plain terms, something very like the dark volcanic plains on our own moon, at 1040 Kelvin, under a red sun that never moves. It is worth being precise about what a non-detection of this quality means, because non-detections have a reputation for being weak results, and this one is not. Measuring zero heat redistribution is the strongest atmospheric constraint available, short of resolving the surface directly. A tentative detection can be argued about. A phase curve with no offset and no nightside emission removes an entire class of possibilities at once. Kreidberg's team did not find a thin atmosphere and call it uncertain. They found the specific pattern that only appears when there is nothing there. In 2026, the James Webb Space Telescope returned to it. A MIRI low-resolution spectrum from 5 to 12 microns, taken across 3 separate secondary eclipses, produced a dayside spectrum that is featureless. No molecular bands. No absorption. Nothing above the surface to leave a mark on the light. A program led by Sebastian Sieber had gone looking for signatures in the regolith itself, and what came back was flat. One more thing about the surface is worth saying plainly. A basaltic or ultramafic composition is not a guess pulled from nowhere. Those rock types have distinctive reflectance behavior, and a dark, low albedo surface at this temperature narrows the field considerably. What the models describe is a plain of solidified lava, unweathered, unbroken by any process involving water or wind, and lit permanently from one fixed direction. Nothing has moved on that surface since it cooled, because there is no mechanism left that could move it. There is a reason this result matters more than one small planet ought to. Dwarfs are the most common stars in the galaxy. Something like 3/4 of all stars are red dwarfs, and the planets we can most easily study around them are exactly the kind that LHS 3844b represents: small, rocky, and orbiting very close in. If those worlds cannot hold on to air, then the majority of planets in the Milky Way are bare stone. That is not a settled conclusion, and other systems on this list push back against it. But this planet is one of the cleanest data points we have, and it points one way. What makes it belong on a list of worlds we can never visit is not the temperature, which is survivable inside a suit, and not the distance, which is small in this company. It is the completeness of the emptiness. There is no air to sample, no weather to record, no surface chemistry doing anything interesting, and no night side worth crossing to, because the night side emits nothing at all. 2 telescopes, 7 years apart, looked at that hemisphere and measured darkness both times. 49 light-years is close enough that we could describe the color of its rock. It is also close enough to make clear that proximity buys us nothing whatsoever. The next world does have an atmosphere, and what condenses in it is the mineral we cut into rings. Number 18, where it rains sapphire, and where the weather report was withdrawn. This planet was discovered twice, by accident of geography. In 2008, the HatNet survey found a transiting giant around a bright F star, and Pal and colleagues published it in the Astrophysical Journal as HAT P7b. HatNet was not a great observatory. It was a network of small, automated telescopes, several of them sitting on the roof of a building, and it found planets by staring at wide fields of sky night after night and looking for the same star to dim in the same way at regular intervals. Then Kepler launched, pointed itself at a patch of Cygnus and Lyra, and that patch happened to contain this system. So the planet acquired a second name from a second mission, Kepler 2b. 1 world, 2 catalogues, and a great deal of data. The Gaia parallax puts it at 333 parsecs, which is 1,086 light-years. The period is 2.204737 days. The mass is 1.806 Jupiter masses, the radius 1.64 Jupiter radii. The host is an F6 dwarf at 6,532 Kelvin, hotter and brighter than the Sun, about 2 solar radii across. In August of 2009, a measurement was published that told us something about this planet's history rather than its present. The technique is called the Rossiter-McLaughlin effect, and it works like this. As a planet crosses a rotating star, it covers first the limb that is turning toward us, and then the limb that is turning away, and that produces a small, characteristic distortion in the star's spectrum during transit. From the shape of that distortion, you can recover the angle between the planet's orbit and the star's spin. For HAT P7b, the answer was that the two are severely misaligned and probably retrograde. The planet goes around backwards relative to the direction its own star turns. Nothing in the standard picture of planet formation produces that. Planets condense out of a flat disk that inherits the star's rotation, so orbits should start out aligned and stay that way. A retrograde orbit around an F star is a fossil. Something massive came close enough to flip the orbit over and then left, and there is no trace of it in the system now. The planet is extraordinarily dark. Its geometric albedo is below 0.03, which means it absorbs more than 97% of the visible light falling on it. Hold that beside a lump of coal, which reflects around 4 or 5%, and the planet is the darker of the two. It is also glowing. The model dayside temperature sits somewhere between 2,630 and 2,880 Kelvin, so the darkness is not the darkness of a cold object. It is the darkness of something so hot that its own materials have stopped reflecting and started emitting. Kepler also detected something in the light curve that has nothing to do with the planet's own brightness. It found ellipsoidal variations, which means the star itself is measurably not round. The planet's gravity raises a permanent tidal bulge on the star, and as that egg shape turns, the amount of surface facing us changes and the total light changes with it. That signal is in the photometry. It is not an inference. A star 2 solar radii across is being visibly deformed by a planet. Kepler stared at this system continuously for 4 years. That is worth stating as a fact about the data, rather than the mission, because it is one of the longest uninterrupted looks anyone has ever taken at any planet other than our own. 4 years at a period of 2.2 days is more than 650 transits, every one of them recorded at the same cadence by the same instrument. Very few objects on this list have that kind of coverage, and the ones that do are the ones where the arguments become most detailed, precisely because there is enough data to argue with. Now to the chemistry, which is what this world is best known for. At 2.5 to 3,000 Kelvin, the things that condense out of an atmosphere are not water and ammonia. They are minerals. Condensation models for HAT P7b predict clouds of aluminium oxide, which mineralogists call corundum. With a trace of chromium, corundum is ruby. With a trace of iron and titanium, it is sapphire. Those clouds form on the night side, where the temperature drops low enough for aluminium oxide to leave the gas phase, and then they precipitate. That is a genuine prediction out of condensation physics, not a figure of speech. A detailed cloud and chemistry mapping study published in Astronomy and Astrophysics in 2019 worked out where on the globe each mineral would come out of the air. The temperature difference across the planet is what drives all of this. On the day side, aluminium oxide stays in the gas phase, along with a great deal of vaporized metal. As that gas is carried around the limb by whatever circulation exists, it cools, and the condensation sequence runs in reverse. Heavier and more refractory compounds come out first, lighter ones later, and each one has its own altitude at which it forms. The result, in the models, is a layered night-side cloud structure sorted by mineralogy, with the corundum sitting at a specific level determined by nothing more exotic than the temperature at which aluminium oxide stops being a gas. There is a second consequence of that circulation that shows up in the light. Because the condensates form on one side and not the other, the planet is not uniformly reflective. Some of the extreme darkness measured on the day side may come from the absence of any condensate deck there at all, leaving nothing to scatter light back. That is a chain of reasoning, not a direct observation, and it is the kind of chain that the 2022 reanalysis should make anyone slightly more careful about. And now the part that requires care, because this planet was once the subject of the first weather report ever issued for another world, and that report has since been withdrawn. In 2016, David Armstrong and colleagues published in Nature Astronomy an analysis of years of Kepler photometry showing that the peak of the planet's phase curve shifted position over timescales of tens to hundreds of days. The interpretation was elegant. If the brightest point on the planet moves, the winds must be changing speed, and the cloud decks must be forming and dissipating. It was reported as changing weather on an exoplanet, and it was, at the time, entirely reasonable. In 2022, Anne Lally and Andrew Vanderberg published a reassessment in the Astronomical Journal. They reproduced the apparent variation, and then they traced where it came from. The signal was an artifact of the light curve flattening method combined with residual low-frequency noise, and the source of that noise was the star. F-stars undergo supergranulation, which is the slow boiling of their outer layers on timescales of days. It is the same physics that produces granules on the Sun, scaled up to a larger, hotter star. And on HAT P7, supergranulation happens to dominate right around the planet's orbital period. Their conclusion was that the shifting phase curve offsets are likely not atmospheric variability at all. One further detail belongs here because it will matter again later on this list. HatNet found this planet from the ground with small telescopes in 2008. Kepler then observed the same system from space for 4 years. 2 entirely independent data sets, 2 entirely different instruments, and the disagreement that eventually arose was not between them. It was between two ways of processing the same Kepler photometry. That is the shape most modern exoplanet disputes take. The observation is rarely in question. What is in question is the chain of decisions between the raw counts and the published number. No just observation has settled it either way. So the honest position, and the one this list will keep returning to, is that for 6 years this world had weather, and a careful reanalysis of the same data took the weather away. The corundum clouds remain a prediction from chemistry. The moving clouds were a prediction from a light curve, and a number and a reduction are not the same thing. The next world is falling into its star, and we can now measure how fast in milliseconds per year. Number 17, the 16-hour year. The Transiting Exoplanet Survey satellite found this one, and Ian Wong and colleagues published it in the Astronomical Journal in 2021. The announcement went out through MIT that November under a title that does not need improving: an ultra-hot gas giant on a 16-hour orbit. The system sits about 861 light-years away, and it is called 2WINE-2109. The orbital period is 0.672 days. Written out, that is 16 hours and 8 minutes. It is the shortest known period for a hot Jupiter orbiting a sun-like star, and the number that gives it meaning is not the period itself, but the separation. The planet orbits at less than 2.3 stellar radii from the center of its star. Put another way, the gap between the planet and the star's surface is smaller than the star's own width. This is not a planet in an orbit. This is a planet skimming. The mass is roughly 5 Jupiter masses and the density about 2.5 grams per cubic centimeter, which is denser than Jupiter and denser than water, and tells you the planet is substantial rather than puffed up. The host is an F-type star of about 1.45 solar masses at roughly 6,500 Kelvin, so it is larger, hotter, and more luminous than the Sun, and the planet is sitting almost against it. The equilibrium temperature is 3,646 Kelvin, plus or minus 88. That makes it the second hottest gas giant known, behind only Kelt 9b. To put 3,600 Kelvin in a frame you can hold, iron melts at 1,800 Kelvin and boils at 3,134. This planet's dayside is hotter than the boiling point of iron. It is hotter than the surfaces of a great many red dwarf stars. If you removed the star from the picture entirely, the planet would still be glowing, on its own, the color of a furnace. The dayside brightness temperature measured on the sky is about 3,630 Kelvin, so the model and the observation agree. The night side has no measurement at all, only an upper limit of 2,400 Kelvin, which means the heat does not make it all the way around. The night side upper limit deserves a second look, because 2,400 Kelvin is not cold. It is roughly the temperature of molten iron in a foundry, and it is the coolest place on the planet. The measured gradient on that hemisphere runs to something in the region of 700 Kelvin per unit of log pressure, which is among the steepest atmospheric temperature gradients recorded anywhere. What that means physically is that the atmosphere on the dark side is stratified almost violently, with layers that are not exchanging heat with one another. Circulation on this planet is inefficient in a way that is unusual even among ultra-hot Jupiters, and the reason is thought to be that the material is being ionized, and ionized gas in a magnetic field does not flow freely. In 2025, Louis-Philippe Coulomb and colleagues published a dayside and nightside retrieval in astronomy and astrophysics, and the results are unusually specific for a planet this far away. On the dayside, they detected neutral ion in emission at a signal-to-noise of 4.3. and carbon monoxide at 6.3. They also found a thermal inversion layer, which means the atmosphere gets hotter as you go up, rather than cooler. Earth's troposphere does the opposite. Climb a mountain, and it gets colder. On TOI 2109b, the upper atmosphere is being heated directly by the star, faster than the lower atmosphere can radiate, and the temperature gradient runs the wrong way. The fact that the iron is seen in emission rather than absorption is the fingerprint of that inversion. Absorption happens when a cool gas sits in front of a hot source. Emission happens when the gas itself is the hottest thing in the line of sight. On this planet, vaporized metal is the hottest thing in the line of sight. There was no significant water on the day side, and that absence is not a mystery. At 3,500 Kelvin, water molecules simply come apart into hydrogen and oxygen. The molecule does not survive the temperature. On the night side, the retrieval found no line features at all. Stand for a moment at the boundary. On a world locked to its star, there is a permanent line where day meets night, and on this planet, that line is not a soft dawn. Behind you, the sky is empty and dark and cooling towards something in the region of 2,400 Kelvin, which still glows. In front of you, the star occupies something close to a third of the visible sky. It does not rise and it does not set. It sits there, enormous and unmoving, a wall of light with a visible curve at its edge, and it fills your entire forward view from the ground to well above where a horizon would be. The air above you is not air. It is iron vapor and carbon monoxide, and it is hotter than the ground you are standing on, which means the light comes from above as well as from ahead. There is no wind you could stand against, because the heat is not being carried anywhere efficiently enough to make one. Everything here is at 3,500 Kelvin, and everything here is glowing, and nothing at all moves except the planet itself, going round once every 16 hours, which you would have no way of noticing, because from this spot, nothing in the sky ever changes. 16 hours is short enough to be worth converting. The planet completes more than 500 orbits in the time Earth takes to complete one. It has gone around its star more times since its discovery in 2021 than Earth has gone around the Sun since the last common ancestor of everyone alive. And each of those laps takes it through the outer reaches of the star's own magnetic environment, which is not a passive place. The planet is not merely close to the star. It is inside the region where the star's field is still doing work. The last thing about this world is that it is falling, and the story of how fast is a good lesson in reading numbers. When the discovery was announced in 2021, press coverage quoted a possible orbital decay rate of anywhere from 10 to 750 milliseconds per year. That is a range spanning a factor of 75, and a range that wide is not a measurement. It is a statement about what the data could not yet exclude. The higher end of it implied a planet visibly spiraling in on a timescale of a few million years, and that is the version that traveled. In July of 2025, a transit timing analysis was published in the Astrophysical Journal that actually measured it. The value is -2.616 milliseconds per year, plus or minus 1.285. That sits consistently against a tidal prediction of -4.186, plus or minus 0.797, and it sets a lower bound on the star's tidal quality factor above 3.7 times 10 to the 7th. The honest summary is that the decay is tentatively detected at the very low end of what was once quoted, and the star turns out to be more efficient at holding on than the dramatic version assumed. That does not make the planet safe. Ultra-short-period Jupiters are rare because they are short-lived, and finding one at all means catching a system near the end of a process rather than in the middle of one. Something in the region of a few tens of millions of years from now, Tidal forces will finish what they have started, and there are only so many ways that ends. But the measurement of it comes down to a few milliseconds a year, extracted from the arrival times of transits recorded over roughly a decade, and that is the actual state of the evidence. There is one loose thread. An astronomy and astrophysics paper in 2024 reported hints of a close outer companion to 20Y2109b. It remains unconfirmed. If it is real, it changes the dynamical picture, because a second body would be a source of the perturbation that put the first one where it is. The next world is almost exactly Earth's size, and something is keeping its interior molten. Number 16. The world needed by its neighbor. On the 17th of May 2023, a paper appeared in Nature with a title that describes the object completely: a temperate, Earth-sized planet with tidally heated interior transiting an M6 star. The lead author is Merrin Peterson, and the detection combined TESS with Spitzer and a network of ground-based telescopes using two different methods at once. Some of the evidence is transits. Some of it is transit timing variations, which is a subtler thing and matters for what follows. The system lies about 86 light-years away in the constellation Crater. The planet is LP 791-18d, and the first thing to say about it is how ordinary its numbers look. The orbital period is 2.75485 days. The radius is 1.03 Earth radii. Eric Gaidos and colleagues, writing in the Astronomical Journal in 2025, cut the mass uncertainty by more than half and give 0.91 Earth masses, plus or minus 0.19. So, within a few percent of Earth's width, and within 10% of Earth's weight. Of the 20 worlds on this list, this is the one that most resembles the planet you are on. The host star does not resemble the Sun at all. It is an M6 red dwarf, small and cool and dim, and the planet's temperature runs somewhere from around 27 to 127 degrees Celsius. That range straddles the boiling point of water at sea level, which is precisely why the object attracted attention. The planet is tidally locked, one face permanently toward the star, and condensation of water on the permanent night side is considered plausible. That last point inverts the usual assumption in a way worth pausing on. When people imagine a habitable world, they imagine a day side. On a tidally locked planet, the day side is the sterilized one, and the only place where liquid water could sit is the hemisphere that has never seen the star. If there is anywhere on LP 791-18d where water pools, it is in permanent darkness. It is worth being clear about how the second planet was found, because it was not found the way most planets are. Transit timing variation means that a transit does not arrive exactly when the clock says it should. If a planet is alone, its transits are metronomic. If something else is pulling on it, the transits run early on some laps and late on others, and the pattern of early and late encodes the mass and orbit of the thing doing the pulling. On this system, the timing variations are what revealed the interaction between planet C and D, and therefore the mechanism that makes planet D interesting at all. Nobody watched the two planets tug on each other. They watched a clock run slightly fast and slightly slow, and worked backwards. Now to the reason this world is on a list of mysterious places, rather than a list of promising ones. Interior to it, closer to the star, sits another planet, LP 791-18c, A sub Neptune. The two of them pass each other regularly, and every time they do, the inner planet pulls on the outer one. That gravitational interaction does something specific. Left alone, a close-in orbit circularizes. Tides raised by the star drain the eccentricity away, the ellipse relaxes into a circle and the planet settles. The Neighbour will not let that happen. It keeps pumping the eccentricity back up, and so the orbit stays slightly out of round, permanently. An out-of-round orbit around a close star means the tidal force on the planet changes through every lap. The planet is stretched when it is nearer and released when it is farther, over and over, for as long as the arrangement lasts. That flexing does not come free. It heats the interior continuously from the inside. The prediction in the Discovery paper is that LP 791-18d should be as volcanically active as Io. CO is the innermost large moon of Jupiter, and it is the most volcanically active body in our solar system by an enormous margin. It has around 400 active volcanoes. Its surface is repaved so frequently that impact craters essentially do not survive on it. And the mechanism keeping it molten is exactly the one described above. Io is locked into a resonance with Europa and Ganymede. That resonance forces an eccentricity that would otherwise damp away, and Jupiter's tides then work on the eccentricity. Io's forced eccentricity is only about 0.0041. That tiny departure from a circle flexes the moon by roughly 100 meters and delivers something in the region of 100 terawatts of heat. The point of the comparison is that tidal heating does not require a large eccentricity. It requires a persistent one. And a persistent one requires a neighbor. There is a consequence that follows directly. Heat delivered continuously to an interior has to leave, and on a rocky planet, the way it leaves is through the surface. Sustained internal heating implies sustained volcanic outgassing, and outgassing is how a rocky planet acquires an atmosphere in the first place. That is why this particular world matters more than its size suggests. If an atmosphere were detected there, it would be the first evidence that a temperate rocky planet around a red dwarf can hold one. That question is the largest open question in the search for habitable worlds, and it is not rhetorical. Red dwarfs are the most common stars in the galaxy. Their habitable zones are close in, which makes planets there easier to find and easier to study. But close in also means exposed to flares, to stellar wind, and to the kind of erosion that stripped the world at number 19 on this list down to bare stone. If red dwarf planets cannot keep their air, then the majority of potentially temperate real estate in the Milky Way is empty. If they can, the arithmetic changes completely. There is one more reason an Earth-sized planet was detectable here when it would have been invisible around a larger star. An M6 dwarf is small, perhaps a fifth the diameter of the Sun. A planet the size of Earth crossing a disk that small blocks a comparatively large fraction of the light, so the transit is deep enough to be seen. Around a Sun-like star, the same planet would produce a dip of roughly 1 part in 12,000, which is at the edge of what any current instrument can do reliably. The reason nearly every small planet we know well orbits a red dwarf is not that red dwarfs make more of them. It is that red dwarfs make them visible. Now the caveat, and it is a real one, because the entire volcanic picture rests on a single number that has two very different published values. The eccentricity is what sets the tidal heating, and the eccentricity depends on which assumption you feed the model. If you apply a tidally damped free eccentricity prior, meaning you assume the system has settled the way theory says it should, the value comes out at 0.0011. That is effectively a circle, and it produces very little heating. If you do not apply that prior and let the data speak, the value is 0.056. That is more than 50 times larger, and it is also far higher than N-body simulations of the system predict when you include both dynamical excitation and tidal damping. So the volcanism case rests on which of those two numbers is correct, and nobody currently knows. This is a good example of something that recurs throughout this list. The observation is solid, the object is real, and the interesting property is a modeled quantity that depends on a choice. A test exists and has already been run. A juiced Cycle 3 program using MIRI was designed to observe 5 secondary eclipses at 15 microns, specifically to distinguish a bare rock from a carbon dioxide-rich atmosphere at 4 sigma. The observations were taken. The results are not yet published. There is a further layer of theory sitting underneath all of this. An astronomy and astrophysics paper in 2025 examined how the oxidation state of the planet's interior governs whether a secondary atmosphere survives at all. A reduced interior outgasses different molecules than an oxidized one, and some of those molecules are far more vulnerable to being stripped away than others. So even if the volcanism is real, whether it produces a lasting atmosphere depends on chemistry nobody can measure from here. If this world has an atmosphere, then the most common kind of planet around the most common kind of star may be habitable after all. The observation that decides it has already been taken, and it is sitting in an archive, waiting for someone to finish the analysis. The next world is the one that started all of this, and it is the reason we know any of these places have air. Number 15. The first air anyone ever smelled on another world. On the 9th of September 1999, a star in Pegasus called HD 209458 got about 1.5% fainter for a few hours, and then went back to normal. 2 teams caught it within days of each other, working with David Charbonneau and Gregory Henry. The radial velocity detection had come first, and David Latham's group held the data that made the prediction possible. They knew there was something there. They knew roughly when it should pass in front, and they pointed telescopes at the right star at the right time. Everything in this field that came afterwards descends from that measurement. Before it, every known planet beyond the Sun was a wobble in a spectrum. You could infer that something was pulling on a star, and you could estimate a minimum mass, and that was all. You had no radius. Without a radius, you have no density, and without a density, you have no idea whether the object is a ball of gas, a ball of rock, or a ball of ice. The transit gave a radius. From that night, planets stopped being numbers and became objects with sizes. The star is 157 light-years away, and it is a G0 main sequence star, which is to say very nearly a copy of the Sun. The planet's period is 3.524736 days. Its mass is around 0.69 Jupiter masses, and its radius is 1.38 to 1.39 Jupiter radii. That combination produced the first genuine surprise. The planet is 35% wider than Jupiter while carrying only 2/3 of Jupiter's mass. It is inflated. Something is holding it puffed up against its own gravity, and a quarter of a century later, the physics of why hot Jupiters do this is still not fully settled. Various mechanisms have been proposed, involving tidal heating, atmospheric circulation depositing energy at depth, and ohmic dissipation from ionized winds moving through the planet's magnetic field. None has been established as the answer. One of the very first properties measured on the very first transiting planet remains unexplained. It is worth understanding why a 1.5% dip was detectable in 1999, when far more capable instruments today struggle with signals 100 times smaller. The planet blocks roughly 1 part in 70 of the star's light. That is a large signal by any standard, large enough that amateur astronomers have since recorded it with modest equipment from suburban gardens. The difficulty was never sensitivity. It was knowing where to point and when. Without the radial velocity work that came first, nobody would have had a reason to watch that particular star on that particular night, and the dip would have gone on happening every 3.5 days, unobserved, as it had been doing for billions of years. There is a second consequence of the radius that took longer to appreciate. Once you have a radius and a mass, you have a mean density, and the mean density of this planet is around 1/3 of a gram per cubic centimeter. That is less than half the density of water and roughly 1/4 of Jupiter's. It settled, immediately and permanently, the question of what these close-in giants actually were. Some astronomers had wondered whether the short-period objects found by radial velocity might be stripped stellar cores or exotic dense bodies of some kind. They were not. They were gas, and there was a great deal less of it packed into a great deal more volume than anyone expected. In 2001, sodium was detected in its atmosphere. That deserves to be stated slowly, because of what it required. Sodium was chosen because its spectral doublet is strong and narrow. They are the same lines that make sodium street lamps orange, and their strength is why they were the first thing anyone went looking for. The method is simple in principle and demanding in practice. During transit, a small fraction of the starlight reaching us does not come straight from the star. It passes through the ring of atmosphere around the planet's edge on its way past, and any molecule or atom in that ring absorbs its own particular wavelengths. Compare the spectrum during transit to the spectrum outside transit, and the difference is the planet's air. It was the first detection of an atmosphere on any planet outside our solar system. 2 years later, in 2003, observations at Lyman Alpha, which is the strongest ultraviolet line of hydrogen, showed something stranger. The absorption was far larger than the planet's own disk. In visible light, the planet blocks around 1.5% of the star. In hydrogen, it was blocking something closer to 15. The hydrogen cloud was enormously bigger than the planet inside it, and the implied escape rate had a lower limit of 10 to the 10th grams per second. 10 million tons a second, leaving. Then in 2004, the European Space Agency and the European Southern Observatory announced carbon and oxygen in that escaping envelope. This is a detail that matters. Hydrogen escapes easily because it is light. Carbon and oxygen are 16 and 12 times heavier, and they should not be able to leave on their own. Finding them in the outflow means the hydrogen is not just leaking. It is streaming out fast enough to drag heavier atoms along with it, like dust caught in a draft. That process has a name: hydrodynamic escape, and this planet is where it was first seen. That result created a class of object nobody had needed before: the Chthonian planet, the stripped remnant core of a gas giant that has lost its entire envelope. HD 209458b earned a nickname from it. It is called Osiris, after the Egyptian god who was dismembered. It is worth noting, in the interest of accuracy, that the escape rate is enormous in absolute terms, but small against the planet's total mass. Osiris is not going to be stripped bare within the lifetime of its star. The nickname is about the process, not the schedule. In 2010, Ignace Snellen and colleagues published a measurement in Nature that still sounds implausible when stated plainly. They measured the wind. The technique used carbon monoxide absorption lines observed at very high spectral resolution during transit. Because the planet is moving along its orbit, its lines are Doppler shifted relative to the stars, and that shift changes through the transit in a predictable way. What Snellen's team found was that on top of the orbital shift, the carbon monoxide lines were blue shifted by about 2 kilometers per second, plus or minus 1, relative to the star's systemic velocity. Blue shift means motion toward us. Gas was flowing from the hot day side, around the limb, toward the night side, and that flow was measured from 157 light-years away. The instrumental requirement for that measurement is worth stating. To see a 2 km/s shift in a spectral line, you need resolving power in the tens of thousands, and you need enough photons to define the line's center to a small fraction of its own width. Creers on the Very Large Telescope could do it, on a bright star, during the few hours a transit lasts, a handful of times. Every one of those constraints is why this planet, rather than a more interesting one, became the place where high-resolution exoplanet spectroscopy was invented. The same observation did something else valuable. By measuring the planet's own orbital motion directly, it recovered the absolute mass without needing to assume the orbital inclination. For a transiting planet, the inclination is already well constrained, so that was not the point. The point was the demonstration that it could be done at all. The modern chapter belongs to JUICT. NIRCam transmission spectra were taken on the 10th and the 16th of November 2022, and the analysis by Shui and colleagues appeared in the Astrophysical Journal Letters in 2024. The findings: supersolar metallicity, meaning the atmosphere is enriched in elements heavier than helium compared with its star. A very low carbon-to-oxygen ratio. Carbon dioxide detected. And no evidence for methane, hydrogen cyanide, or acetylene. That carbon-to-oxygen ratio is a fingerprint of where the planet was born. Different molecules freeze out at different distances from a young star. A planet that assembles beyond the water ice line and then migrates inward acquires a different chemical signature from one that forms where it now sits. A very low carbon-to-oxygen ratio points to formation out in the cold, followed by a journey inward. The planet's chemistry is a record of a trip it took 4.5 billion years ago. Independently, Creyers Plus, working from the ground across 4 transits, published in Astronomy and Astrophysics in 2024, detected water and reported the same set of non-detections. That agreement matters more than either result alone. A ground-based spectrograph fighting through Earth's own atmosphere reached the same conclusions as a space telescope with none in the way. In 2025, a reanalysis of the combined Hubble and JUICT spectra using the SANSAR retrieval framework appeared in the Astronomical Journal, continuing a sequence of reanalyses that now stretches across 3 decades. There is one number about this planet that explains why it, specifically, has been the site of so many first-ever measurements. The star is bright. It is bright enough to be used as a spectroscopic reference, which means long exposures produce high signal-to-noise without the observation becoming a heroic effort. There are more extreme planets, hotter ones, stranger ones. Almost every one of them is orbiting something too faint to study properly. Osiris was in reach, and so it became the laboratory. And of course, it is not in reach at all. 157 light-years is not a distance anything built by us will ever cross. We know the composition of that planet's air, the direction its wind blows, the rate at which it is losing hydrogen, and the region of its own system where it was assembled. We will never send anything there. Every fact on this list about the air of another world traces back to one night in 1999, when a star dimmed by 1% and a planet stopped being a number. The next world should have been stripped bare by now, and somehow it has not been. Number 14. The Forbidden Planet. There is a region of parameter space that planets are not supposed to occupy, and it has a name. It is called the Neptunian Desert, and it is not a theory. It is a hole in a scatterplot built from thousands of confirmed worlds. Put orbital period on one axis and planet mass on the other. Plot everything we have found, and a gap appears. At periods under about 2 to 4 days, planets of roughly Neptune's mass essentially do not exist. The physics behind the gap is straightforward. A Neptune mass planet is mostly a hydrogen and helium envelope wrapped around a modest core. At that distance from a star, the ultraviolet and X-ray output during the star's early active life should heat the upper atmosphere until it escapes, and keep doing so until the envelope is gone. What is left behind is a bare core, which lands somewhere else on the plot entirely. Planets in the desert should not survive their own youth. It is worth being clear about what kind of claim a statistical desert is. It is not a prediction that was made and then confirmed. It is a pattern that emerged from data as the catalogue of known planets grew large enough for patterns to be visible at all. Through the 2000s, when only a few hundred planets were known, the gap was not obvious. By the middle of the 2010s, with thousands catalogued by Kepler and then TESS, it was unmistakable. That history matters, because it means the desert is an empirical fact first and an explanation second. The photoevaporation account is the best available reason for the hole. It is not the reason the hole was noticed. The consequence is that a single occupant of the desert carries more weight than a single planet normally would. Most discoveries add a point to a distribution. This one sits in a place where the distribution says there should be nothing, and so it constrains the explanation rather than the census. Then TS4b is in the desert, and it still has its atmosphere. It was found by the Next Generation Transit Survey at Paranal Observatory in Chile, and published in monthly notices of the Royal Astronomical Society in 2019. Richard West at the University of Warwick led the discovery, working with Peter Wheatley, Daniel Bayliss, and James McCormack. It carries a second designation from the TESS catalogue, TOI 1926b. It lies about 922 light-years away. The orbital period is 1.337350 days. The semi-major axis is 0.019 astronomical units, and the orbit is circular. The mass is 20.6 Earth masses, plus or minus 3, and the radius is 3.18 Earth radii, plus or minus 0.26. That makes it about 20% smaller than Neptune. The host is an early K dwarf at 13th magnitude, and the planet's equilibrium temperature is around 1000 degrees Celsius. 20 Earth masses at 1000 degrees, orbiting once every 32 hours, is precisely the combination that should not be there. And yet the transit is real, the mass is measured, and the radius is too large for the object to be a bare core. There is gas around it. There is a detail in that 32-hour orbit that is easy to pass over. At 0.019 astronomical units, the planet is roughly 3 million kilometers from its star. The star is an early K dwarf, somewhat smaller and cooler than the Sun, but at that separation it would still fill a substantial fraction of the sky, and the planet's upper atmosphere sits inside the region where the stellar wind is still dense. Whatever is holding that envelope down is holding it down against a constant outward pressure, not merely against the planet's own tendency to leak. The discovery paper offers two explanations and declines to pick between them, which is the right posture and worth reproducing on air. The first is that the planet has an unusually massive core. A larger core means stronger gravity at the base of the envelope, and stronger gravity means the escaping gas has more work to do to get away. Push the core mass high enough, and the envelope survives. If that is the answer, then NGTS4b is a Neptune in appearance only. Underneath, it would be mostly rock and iron, wearing a thin skin of gas that happens to be inflated enough to look substantial from here. The second is that the planet arrived late. Stars are at their most violent in their first few 100 million years, when their X-ray and ultraviolet output is orders of magnitude above what it will settle down to. A planet that spends that period farther out, in a gentler orbit, and only migrates inward afterwards, never experiences the phase that would have stripped it. If that is the answer, then the planet is old, and its orbit is young, and what we are looking at is a world that arrived after the danger had passed. There is no way at present to distinguish between them from the data in hand. The detection itself is worth its own moment, because it set a record that has nothing to do with the planet's strangeness. The transit depth is 0.13%, plus or minus 0.02. In magnitudes, that is about 1.3 millimagnitudes. It is the shallowest transit ever detected from the ground. To appreciate that, consider what ground-based photometry is fighting. Every measurement has to pass through Earth's atmosphere, which is turbulent, which changes transparency from minute to minute, and which scatters light in ways that vary with the position of the star in the sky. Space telescopes do not have this problem, which is why Kepler and TESS dominate the small planet catalogues. UNGTS was designed specifically to push ground-based precision down into the range where sub-Neptunes become detectable, using 12 20-centimeter telescopes working together at a site chosen for its stability. It sits at Paranal, the same mountain as the Very Large Telescope, and it reached 1.3 millimagnitudes on a 13th magnitude star. That precision is also why some databases still list NGTS-4b as unconfirmed. The signal sits at the very edge of what 1-meter class telescopes can independently verify, and the discovery paper itself notes that following it up from the ground is challenging even with the best available instruments. Nobody has published a formal false positive claim. But the object lives in a category that is uncomfortable for a field that prefers its detections comfortable. The reason it belongs on this list is not that it is dangerous. Compared with most of what comes before and after, it is unremarkable. It belongs here because it is a planet that has kept something it should have lost, in a place where nothing like it survives, and we have exactly 2 candidate explanations, no way to choose between them, and no prospect of ever going to look. The next world had an atmosphere announced, doubted, and then quietly taken back. Number 13. The atmosphere that was announced, doubted, and withdrawn. This is the item on the list where the mystery is not about the planet. It is about how we come to know things and how often the answer changes. GJ1132b was found in 2015 by the Mirth-South Array, a set of small robotic telescopes designed to monitor nearby red dwarfs 1 star at a time. Zachary Berta Thompson and colleagues announced it that November. It orbits an M dwarf about 41 light-years away in Vela, which makes it one of the nearest rocky planets known to us. Mirth itself is worth a sentence, because it is an unusually direct piece of engineering. Rather than staring at a wide field and hoping, it points a small telescope at one nearby red dwarf at a time and watches it for as long as necessary before moving on. The logic is that the nearest small stars are the only ones around which an Earth-sized planet produces a transit deep enough to see from the ground, so there is no point surveying anything else. The array in the southern hemisphere found this planet doing exactly what it was built to do. The numbers on it are unusually good for a small world, and the reason is the star. The host is small, about 0.18 solar masses and 0.21 solar radii, at 3,270 Kelvin. It is quiet, and it rotates slowly, which for once makes life easier rather than harder. Magnetic activity is the thing that ruins mass measurements, and this star does not have much of it. So, the planet's radius is 1.13 Earth radii, plus or minus 0.056. Its mass is 1.66 Earth masses, plus or minus 0.23. The bulk density comes out at 6.3 grams per cubic centimeter, plus or minus 1.3, which is essentially Earth's. The orbital period is 1.6 days, and the equilibrium temperature about 580 Kelvin. A second planet, GJ1132c, at 2.64 Earth masses on a nearly 9-day orbit, was added by HARPS radial velocities in 2018. An Earth-like bulk density at 580 Kelvin tells you the planet is rock and iron. It tells you nothing at all about what sits above the rock. On the 11th of March 2021, Mark Swain and colleagues announced a result that would have been historic. Using Hubble's Wide Field Camera 3, they reported an atmosphere on GJ1132b, and not just any atmosphere. They reported a secondary atmosphere. The distinction matters enormously. A primary atmosphere is the hydrogen and helium a planet captures directly from the disk it forms in. Around an active red dwarf, that envelope is stripped away early. A secondary atmosphere is what comes afterwards, vented out of the interior by volcanism, built from the planet's own rock rather than inherited from its birth. Earth's atmosphere is a secondary atmosphere. Every atom of nitrogen you are breathing came out of the ground. Swain's team reported aerosol scattering, hydrogen cyanide, and methane in a low mean molecular weight atmosphere. Had it held, it would have been the first atmosphere ever detected on an Earth-sized rocky planet anywhere, and the first demonstration that a stripped world can rebuild its air. Understanding why the claim mattered so much also explains why it was scrutinized so hard. Roughly 3/4 of the stars in the galaxy are red dwarfs, and their small size makes their planets uniquely accessible. If those planets are all bare rock, then the great majority of the galaxy's terrestrial worlds are airless, and the search for anything resembling a habitable environment narrows dramatically. If even one of them has rebuilt an atmosphere out of its own interior, the picture opens up again. A single detection was carrying an enormous amount of weight, and results carrying that much weight attract exactly the kind of attention that followed. It did not hold. Two independent groups reprocessed the same Hubble data. Lorenzo Mugnai and colleagues in 2021 and Jessica Libby Roberts and colleagues in 2022 each ran their own reduction, and each found no molecular features. A flat line fit the data best. That is not a marginal disagreement. It is two teams looking at the same photons and finding nothing where a third team had found molecules. In 2023, Just was pointed at it. Two NIR-spec transits were taken on the 25th of February and the 5th of March under a program led by Kevin Stevenson and Jacob Lustig-Jaeger, with the analysis published by May, MacDonald and colleagues. And the result was worse than a non-detection. The two visits disagreed with each other. One looked like a water-dominated atmosphere, with roughly 1% methane, or, equally consistently, like unocculted star spots. The other was featureless. The author's own preferred explanation, stated plainly in their paper, was an unlucky random noise draw. That phrase deserves respect rather than embarrassment. Two observations of the same planet, taken 8 days apart with the same instrument, produced different answers, and the team's honest reading was that one of them had been dealt a bad hand by chance. Writing that down, in a journal, under your name, is harder than announcing a detection. The star spot problem is the deeper issue, and it recurs across this whole field. When a planet transits, You are comparing the star's light with the planet in front of it to the star's light without. That comparison assumes the star is a uniform lamp. It is not. A red dwarf surface is patchy, with cool spots and hot regions, and if the planet happens to cross a patch that is not representative of the whole disk, the difference between the two spectra contains the star's patchiness as well as the planet's air. Unocculted star spots, meaning spots the planet does not cross, can imprint features that look exactly like molecular absorption. Separating the two is the central systematic in small planet spectroscopy, and it has not been solved. In August of 2025, Bennett, MacDonald and colleagues added 2 further NIR spec transits and co-added all 4 together. The combined spectrum is best fit by a flat line. Set that against the mid-infrared emission data from 2024, and only the very thinnest of atmospheres remains permitted by the data. And an atmosphere that thin would not be stable, given the planet's age and the irradiation it receives. Their conclusion, written out, the simplest explanation is that GJ1132b is indeed a bare rock. It is also worth noticing what did not happen. Nobody accused anybody of error in bad faith. The original team published their reduction, other teams published theirs. The disagreement was located in the processing rather than in the observation, and then more data were taken. The whole exchange ran from March 2021 to August 2025, in public, in journals, under names. 4.5 years to settle whether a planet 41 light-years away has air, on a question that will now be quietly cited in review papers and never make a headline again. There is a ground-based coda, CRIERS Plus Transit Spectroscopy in 2025, working under the assumption of a clear hydrogen-dominated atmosphere, detected no molecular species either. That is now 4 independent transit observations across 2 space telescopes and 1 ground-based spectrograph, all pointing the same direction. The mean molecular weight of an atmosphere is the quantity that governs how far it puffs out, and therefore how strong a signal it leaves in a transit spectrum. A light atmosphere, dominated by hydrogen, extends a long way and produces deep features. A heavy one, dominated by carbon dioxide or nitrogen, sits close to the surface and produces almost nothing. That asymmetry is the reason the field can rule out thick hydrogen envelopes with confidence while remaining nearly blind to the kind of atmosphere Earth actually has. A flat spectrum does not prove there is no air. It proves there is no light air, and everything else remains open. It is important not to overstate what has been lost. The secondary atmosphere idea remains sound physics. Rocky planets do outgas, Earth is proof, and the search for the first such atmosphere around another star continues on other targets, including the world at number 16 on this list. What did not survive is this planet's specific claim. For 4 years, the nearest Earth-sized world with an atmosphere was a headline. Then, the slow, unglamorous, largely uncelebrated work of reanalysis took it back. The next world is doing something no other planet has been caught doing. It is attacking the star it orbits. Number 12, the planet that makes its own star explode. Every other world on this list is something the universe is doing to a planet. This one is the reverse. This is a planet doing something to a star. HIP 67522b was found by TESS in 2020 through the TIME survey, led by Aaron Rizzuto, using a custom notch filter pipeline built specifically to find planets around young, magnetically loud stars. Young stars are difficult targets. Their light curves are covered in spots and flares and rotational modulation, and an ordinary transit search drowns in it. The pipeline was written to see through that noise, and it worked. The system lies roughly 415 light-years away in Centaurus, with published distances ranging from 383 to 417, depending on which catalogue you consult. The star is the point of the whole item. It is a G-type star, slightly larger and cooler than the Sun, and it is about 17 million years old. 17 million years is nothing. The Sun is 4.5 billion. This star has completed roughly 1/4% of the Sun's life so far. It belongs to the Scorpius-Centaurus Association, one of the nearest groups of young stars, and it has not finished settling down. It spins fast, its magnetic field is strong and disorganized, and it flares constantly. 17 million years ago on Earth, the Miocene was underway, and apes were spreading through the forests of Africa and Eurasia. The star is younger than that. The planet orbits in about 7 days, with a radius of 10.02 Earth radii, which makes it Jupiter-sized, and a bulk density below 0.1 grams per cubic centimeter. That is roughly 1/10 of the density of water. It is among the lowest densities ever measured for any planet. What that describes is a world that has not finished contracting, still swollen with the heat left over from its own formation, enormous and almost weightless. A density that low is difficult to hold in the head, so it is worth translating. Water is 1 gram per cubic centimeter. Cork is about 1/4 of that. This planet is below 1/10. If there were an ocean large enough to put it in, it would float on the surface with almost all of its volume above the waterline. It has Jupiter's width and a small fraction of Jupiter's substance, and the only reason it holds together at all is that it is still hot inside from the process that assembled it. On the 1st of July 2025, Ekaterina Ilin and colleagues published in Nature the result that puts this planet here. They combined test data with a dedicated Cheops campaign spanning 5 years, and they found 15 flares on the star that cluster near the planet's transit phase. That clustering is the entire argument, and it is a statistical one. Flares on a young star are common. That is not news. What is news is that these flares are not distributed randomly around the orbit. They happen preferentially when the planet is in a particular place. That is the first evidence that a planet triggers flares on its host star, and it had been predicted for decades and searched for repeatedly without the statistics ever holding up. It is worth appreciating what 5 years of monitoring means for a claim like this. 15 flares is not many. Any individual flare proves nothing, because young stars flare all the time, and coincidences are cheap. The result lives entirely in the distribution, where those 15 events fell relative to the planet's position, compared with where they would be expected to fall if the two had nothing to do with one another. Building that distribution required a dedicated space telescope campaign spread across half a decade on a single target, and the answer it produced is a probability, not a photograph. The mechanism the authors describe works through the star's magnetic field. The planet, moving through that field, gathers orbital and magnetic energy and sends alpha waves back along the field lines toward the star. Alpha waves are a real and well-studied phenomenon. They are the same kind of disturbance that carries energy along magnetic field lines in the Sun's corona. The image the team used is a rope being whipped. The planet flicks the rope, the wave travels down it, and it arrives at the star's surface. What happens when it arrives is the interesting part. The wave does not supply the energy for the flare. It sets off a flare that was already primed in a region of the star's magnetic field that was already storing energy and waiting for a trigger. That is how the flares can be more energetic than the wave that caused them, and they are, the observed flares are about 100 times more energetic than theory predicted. The consequence for the planet is direct and unkind. Because it is triggering flares on the star it orbits, and because those flares happen preferentially near it, the planet receives roughly 6 times more radiation than it otherwise would. The damage is self-inflicted. The paper projects that over the next 100 million years, this planet could shrink from nearly Jupiter-sized down to something the size of Neptune, its envelope eroded away by a process it started. Now, the contested part, and here the disagreement is not about the flares. It is about the planet's mass, and it is a factor of 2. Thao and colleagues published a JOST near-spec analysis in 2024 under the title The Featherweight Giant. Through a Bayesian retrieval of the transmission spectrum, they obtained a mass of 13.8 Earth masses, plus or minus 1, and detected water, carbon dioxide, modest carbon monoxide, and weak hydrogen sulfide and sulfur dioxide. 13.8 Earth masses at Jupiter's size is not a hot Jupiter at all. It reclassified the object as a sub-Neptune precursor, a planet on its way to becoming something much smaller. Then in 2026, Lavale and colleagues published an astronomy and astrophysics paper based on 92 volt-Kriers plus spectra taken during a single transit on the 30th of January 2025. Their mass is 29.8 Earth masses, plus or minus 3. That is twice the JOST value, and the 2 results are inconsistent at 3 sigma. Their own phrasing is that this casts doubt on the actual planetary density. The disagreement matters for more than bookkeeping, because the mass is what determines the planet's fate. At 13.8 Earth masses, the envelope is only loosely bound, and the projected shrinkage to Neptune size is comfortable. At 29.8, the gravity is twice as strong at the base of the atmosphere, and the same radiation strips it far more slowly. The 2 measurements describe 2 different futures for the same object, and both were obtained by careful teams using excellent instruments on the same planet. Their spectra contain something else remarkable. They detected water at 20 sigma and carbon monoxide at 5 sigma, and they report a tentative 2 sigma detection of heavy water with a deuterium enrichment of something like 1,000 times the protosolar value. If that survives scrutiny, it would be the first deuterium detection in any exoplanet atmosphere. 2 sigma is not a detection, and the paper does not claim it as one. It is worth knowing that it is sitting there. There is a companion result that belongs here for the sake of completeness. About 135 hours of low-frequency radio monitoring with the Australia Telescope Compact Array found the star bright and bursty, but detected no planet-induced radio flares. That is a clean non-detection, and it is consistent with the nature result rather than against it, because the radio and optical signatures need not track each other. So this is a Jupiter-sized world of uncertain mass, orbiting a star younger than the great apes, whipping that star's magnetic field into explosions 100 times stronger than they should be, and then absorbing 6 times the radiation as a result. It is the only known world that is actively causing its own destruction, and it will not survive the process in anything like its present form. The next world is not being attacked. It is simply coming apart, and the telescope was already pointed at it. Number 11. The world coming apart on camera. Everything that has ever been destroyed in the universe was destroyed before anyone was watching. Stars have collapsed, planets have been swallowed, worlds have been ground down to dust, and almost all of it happened unobserved, because the events are rare and the instruments are few and the odds of the 2 coinciding are terrible. This is the one case where the telescope was already pointed at it. Kepler 1520b was originally catalogued as KIC 12557548b, and Saul Rappaport and colleagues published it in the Astrophysical Journal in 2012 under a title that hedges carefully: a possible disintegrating short-period supermercury. The word possible was doing real work. What Kepler had recorded was a repeating dip in a star's brightness with a strict period, which normally means a planet. But the depth of the dip was different every time. A solid planet cannot do that. A solid body of fixed size crossing a star of fixed size blocks the same fraction of light on every lap, and the transit depth is a constant. This one varied from about 0.2% to 1.3%, passage after passage, with no regular pattern. The physical picture that emerged to explain the variation is worth setting out, because it is not complicated and it is very strange. At 2200 Kelvin, the surface of a small rocky body does not simply glow. It sublimates. Rock goes directly from solid to vapor, and the vapor rises. On a large planet, gravity would pull that vapor back down, and an atmosphere would establish itself. On a body of this size, gravity is too weak to hold it, and the vapor keeps going. Once it is far enough out to cool, it condenses into mineral dust, and that dust is then pushed away from the star by radiation pressure. The result is a comet-like tail made of the planet trailing behind it. That is why the transit depth changes. What crosses the star is not the planet, or not only the planet. It is the planet plus however much dust happens to be in the tail on that particular orbit, and the tail is not stable. It thickens and thins. Kepler was not recording a planet at all in the ordinary sense. It was recording the weather of a disintegration. The confirmation came in 2015 from Boczynski and colleagues using the William Herschel telescope, and the method they used is elegant. They measured the transit depth at several wavelengths simultaneously. A solid object blocks all colors equally because it is opaque. Small dust grains do not. They scatter and absorb light in a way that depends strongly on wavelength. The transit came out color-dependent. Whatever was crossing that star was made of dust. The object was formally confirmed and renamed in the Kepler catalogue release of May 2016. It lies about 2020 light-years away in Cygnus. The host star is a K-type main sequence star, 0.76 solar masses, 0.71 solar radii, 4,677 Kelvin, about 4.5 billion years old, radiating roughly 14% of the Sun's luminosity. Its apparent magnitude is 16.7, which means it is far too faint for any naked eye anywhere, and faint enough that this entire story depends on space-based photometry and a handful of large ground telescopes. The orbital period is 0.6535538 days. That is 15 hours and 41 minutes, and it is measured to 7 decimal places, because Kepler stared at the field continuously for 4 years and recorded more than 2,000 orbits. The orbital radius is about 0.01 astronomical units, and the surface temperature around 2,255 Kelvin. 7 decimal places on the orbital period is worth pausing over as a fact about measurement rather than about the planet. It means the period is known to within about 1/100th of a second. That precision comes from having thousands of transits spread across 4 years, each one anchoring the timing a little more tightly. Very few objects on this list have that kind of coverage, and the ones that do tend to be the ones where the arguments become most detailed, because there is finally enough data to argue with properly. The mass has never been measured. What exists instead is a ceiling derived from the mass loss modeling, and the ceiling is 2% of an Earth mass. That is less than 2 lunar masses. It is roughly the mass of Ceres and Vesta put together. This is a planet in name and an asteroid in substance. The radius is constrained to under 1 Earth radius from limits on the secondary eclipse. Ride behind it for a moment. You are trailing the planet at a distance of a few of its own diameters, moving at something over 200 kilometers per second, with the star a wall of orange light off to one side. The planet ahead of you is small, dark, and difficult to see directly. What you can see is what is leaving it. From the sunward face, material is lifting off in a continuous stream, silicate vapor that rises, cools within a few planetary radii, and condenses into grains a fraction of a micron across. Those grains do not fall back. Radiation pressure and the stellar wind take them, and they stream away behind the planet in a broad, curving trail that is far larger than the planet itself. You are inside that trail. It is not dense. It is closer to a thin haze than to smoke, and the light coming through it is reddened because small particles scatter blue light out of your line of sight before they scatter red. Ahead, the planet is silhouetted against the star. Behind, the trail spreads and thins and eventually disappears, having been carried out of the system entirely. Nothing about this is violent. It is quiet, and it is continuous, and it has been going on for a very long time. The mass loss rate is estimated at between 0.6 and 15.6 Earth masses per billion years, which is a wide range and honestly reported as 1. The planet may already have lost around 70% of its original mass. If that estimate is right, what crosses the star every 15 hours is close to a naked core. Total destruction is projected within roughly 40 to 400 million years. There is a detail in the light curve that is easy to miss and difficult to forget once you have seen it. Just before the transit begins, the star gets very slightly brighter. That is forward scattering. Small grains scatter light, preferentially in the direction it was already traveling, so as the leading edge of the dust cloud comes into the line of sight, some starlight that would have missed us is redirected toward us. It is the same optical effect that makes dust on a windscreen glow when you drive toward the sun. On this system, it happens every 15 hours and 41 minutes, 1,200 light-years away, and Kepler recorded it thousands of times. The composition of the dust is inferred rather than measured. Modeling favors magnesium-iron silicates, and that work was extended in 2023 to cover both this planet and a sibling object, K2-22b, which is doing the same thing. It is inference from how the dust affects light, not a direct chemical detection, and the distinction should be preserved. The destruction is also not smooth. Schlavin and colleagues found in 2016 that the activity had reduced and the particles had grown larger. The transits ran shallow through 2013 and 2014. Then a campaign using the 61-inch Kuiper telescope showed the depths returning to their Kepler-era values, published in 2018 under the title Back to Normal. The planet sheds in episodes, and the intervals between them are not understood. Something turns the tail on and off on a timescale of years, and nobody has explained what. In January of 2025, just mid-infrared observations of the sibling object K2-22b were published, which is the first serious attempt to get a direct compositional handle on this class of object rather than a modeled one. What makes this world belong here is not that it is dangerous, and not that it is far. 2,000 light-years is unremarkable on this list. It belongs here because it is the only planet anyone has ever watched die, and because within a few 100 million years, on a timescale that is short by every astronomical standard, there will be nothing there at all. The star will go on. The dust will have dispersed. And the 15-hour dip that has been recorded thousands of times will simply stop. The next world is not being destroyed by anything. It is just very, very far from the star it belongs to. Number 10. 7,000 astronomical units from home. The discovery here was not of an object. Both bodies in this system had been sitting in survey catalogues for 8 years, each of them logged, each of them with coordinates and a spectral type, neither of them considered interesting. What Niall Deacon, Joshua Schleider and Simon Murphy published in monthly notices of the Royal Astronomical Society in 2016, announced in late January of that year, was not a new body. It was a relationship. They noticed that the two objects were moving through space together. The technique is called common proper motion, and it is the oldest test in the business. Every star drifts across the sky at its own rate and in its own direction, the combined result of its motion through the galaxy and ours. Two unrelated stars that happen to lie in the same line of sight will drift apart measurably over a few years. Two objects that are gravitationally bound will not. They will move as a unit, at the same speed, in the same direction, indefinitely. That is the only practical way to establish that two things separated by a very large distance actually belong to each other. There is something quietly instructive about a discovery of this kind. No new telescope was built for it. No new instrument was commissioned. Both objects had already been observed, catalogued, and filed. What was missing was the act of comparing two entries that nobody had thought to compare, and then checking how they had moved. 8 years passed between the observations and the realization cost nothing but attention. The system lies 111.4 light-years away, plus or minus 0.3, from Gaia. The original press coverage in 2016 quoted about 104, which was the best available figure at the time. The Gaia value supersedes it. Now the number that matters. The separation between the planet mass object and its star is about 7,000 astronomical units. That is roughly 1 trillion kilometers. Neptune orbits the Sun at 30 astronomical units. Pluto averages 39. Voyager 1, launched in 1977 and still transmitting, has been traveling outward for 48 years and has reached something over 160. This object sits at 7,000. It is more than 200 times farther from its star than Neptune is from ours, and more than 40 times farther out than Voyager 1 has managed in half a century. The orbital period is around 900,000 years. That figure is worth holding still for a moment. A single year on this world is longer than the entire history of the human species. Homo sapiens has existed for something like 300,000 years. Anatomically modern humans, agriculture, writing, every civilization that has ever risen and fallen, all of recorded history, every language ever spoken, all of that fits inside a third of one orbit. If this object began a lap when the first stone tools were being made by our ancestors, it would still be less than halfway round. The object itself is spectral type L3, with an effective temperature near 1,800 Kelvin and a mass estimated at between 11.6 and 14.7 Jupiter masses using the Baraf evolutionary models. Its properties closely parallel Beta Pictoris b, which is one of the best studied directly imaged planets we have. Beta Pictoris b orbits at about 10 astronomical units. This object is 700 times farther out. The host is a star called TYC 9486-927-1. It is an active, rapidly rotating M1 dwarf. The system's age is somewhere between 10 and 45 million years, and that youth is the only reason we can see the companion at all. Objects of this mass do not shine by fusion. They glow with the heat left over from their own formation, and that heat fades with time. Give this one another few 100 million years and it will be effectively invisible. The gravitational bond at that distance is genuinely tenuous. At 7,000 astronomical units, the pull of the host star on its companion is roughly 50 million times weaker than the Sun's pull on Earth. Passing stars, giant molecular clouds, and the tidal field of the galaxy itself all exert forces comparable to what is holding this pair together. Wide binaries like this one are routinely broken apart over hundreds of millions of years by nothing more dramatic than the neighborhood drifting past. The arrangement we are looking at is not stable in any deep sense. It is temporary, on a timescale that happens to be much longer than ours. Stand on it, if there were anywhere to stand. The first thing you would notice is the absence of a sun. There is no disk in the sky. The host star, 7,000 astronomical units away, is a point of light, brighter than Venus appears from Earth, bright enough to be unmistakable and utterly useless. It casts no warmth. It casts no shadow you could see. It does not move perceptibly across the sky, because the orbital period is 900,000 years, so its position is fixed for every human timescale you could name, and for every timescale after that. The rest of the sky is stars, and the object under you is not dark. It is glowing dull red at 1,800 Kelvin from its own residual heat, so the ground is the brightest thing in view, lit from underneath by the memory of its own formation. There is no day. There is no night. There is no season, no weather driven by starlight, no external clock of any kind. There is a warm body cooling slowly in the dark, with a bright dot in the sky that it is technically attached to. It is also worth noting how thoroughly this object defeats every mental picture we bring to the word planet. It receives essentially no energy from its star. It has no seasons, no orbit that anything could observe completing, and no meaningful sense in which the star governs its environment. Everything that makes a planet planet-like in our experience comes from the star, and here the star contributes almost nothing but a name. There are two honest caveats, and both belong here rather than in a footnote. The first is that we do not know whether this is a planet. The mass estimate straddles the deuterium burning limit at around 13 Jupiter masses, which is the conventional dividing line between a planet and a brown dwarf. Below it, an object never fuses anything. Above it, it can briefly fuse deuterium early in its life before running out. 11.6 to 14.7 Jupiter masses sits across that line, so the object may be either. And it is worth saying that the line itself is a convention rather than a law of nature. It marks a threshold in nuclear physics, not a threshold in how things form. The second caveat is more interesting. At 7,000 astronomical units, this object almost certainly did not form the way planets form. Protoplanetary disks do not extend that far. There is no plausible mechanism for assembling a body of 10 to 15 Jupiter masses out of material at that distance, because there is no material at that distance. What is far more likely is that the pair formed the way a wide binary forms, from two separate fragments of the same collapsing cloud, and has been loosely bound to each other ever since. One further consequence of that separation deserves stating. Light from the host star takes about 40 days to reach the companion. If something happened at the star, a flare, a change in brightness, anything at all, the companion would not register it for more than a month. In our own system, sunlight reaches Neptune in about 4 hours. Here, the delay is measured in weeks, which means that even the star's own behavior arrives as old news. The Discovery paper's own title hedges precisely, and the hedge is the honest position, a wide, possibly planetary mass companion. So this is an object that may or may not be a planet, orbiting a star it may never have formed with, at a distance where the word orbiting is doing an enormous amount of quiet work. It is bound. It is gravitationally attached. And it is, for every purpose that matters, alone. The next world is not far from its star at all. It falls at it, misses, and is thrown back out. Number 9. The most eccentric orbit ever measured. The Anglo-Australian planet search ran for well over a decade out of Siding Spring Observatory in New South Wales, measuring the velocities of southern stars again and again, year after year, waiting for periods long enough that no short survey could ever find them. On the 14th of March 2006, Hugh Jones and colleagues published a paper from that program with an unglamorous and entirely accurate title, High Eccentricity Planets from the Anglo-Australian Planet Search. One of the objects in it holds a record that has stood for 20 years. It is worth explaining what a radial velocity survey is actually doing, because it shapes what such a survey can find. The instrument measures the star's motion toward and away from us by watching its spectral lines shift, and the shifts involved are small, meters per second, against a star moving through the galaxy at tens of kilometers per second. To detect a planet with a 19-month period, you need observations spread across several 19-month intervals, which means a program that outlives its own funding cycles. Long-period planets are not harder to detect because the signal is weaker. They are harder to detect because someone has to keep pointing the telescope for a decade. HD 20782b lies about 117 light-years away in Fornax. The host is a G-type main sequence star, classified G1.5v in some catalogues and G3v in others, with an age of 8.5 billion years. That is roughly twice the age of the Sun. In every respect that a casual glance would notice, this is an ordinary, mature, quiet star. The orbit is not ordinary. The eccentricity is 0.97 plus or minus 0.01 from O'Toole and colleagues in 2009. Eccentricity is a measure of how far an ellipse departs from a circle. A perfect circle has an eccentricity of 0. Earth's orbit is 0.017, which is close enough to a circle that you would need instruments to notice. Mars, which Kepler used to work out that orbits are ellipses at all, is 0.09. Halley's Comet is 0.97. That last comparison is the point. HD 20782b has the orbit of a comet, and it has the mass of a giant planet. The minimum mass is somewhere around 1 to 2 Jupiter masses, depending on which analysis you take, and the true value depends on an inclination we do not know. The semi-major axis is 1.36 astronomical units, plus or minus 0.12. The period is reported as 585.86 days by O'Toole and 597 days by Stephen Kane and colleagues in 2016. Those two numbers disagree, and the honest thing is to say so rather than pick one. What the eccentricity means physically is a journey. At its closest approach, the planet passes about 0.06 astronomical units from the star. That is well inside where Mercury orbits the Sun. At its farthest, it is out at about 2.5 astronomical units, beyond Mars, and into the region where our own asteroid belt sits. It falls all the way in, whips around the star at enormous speed, and is flung all the way back out, and it does this every 19 months or so. The consequences for the planet are not subtle. Because the intensity of starlight falls off with the square of distance, the energy this world receives at closest approach is roughly 1,700 times what it receives at its farthest point. Nothing in our solar system experiences anything remotely like that. A gas giant undergoing that swing every 19 months does not have a climate in any recognizable sense. It has a cycle of heating and cooling that dominates everything else about it, and the atmosphere never reaches equilibrium with either extreme, because it does not stay anywhere long enough. Most of the planet's year is spent in the cold. That is a property of ellipses rather than of this system specifically. A body on an eccentric orbit moves fastest when it is closest and slowest when it is farthest, so it lingers in the outer part of its path and rushes through the inner part. The transition from beyond Mars to inside Mercury happens over a matter of weeks, and then it is over. There is a further consequence that follows from the shape of the path. A planet on a near-circular orbit is dynamically quiet. It does not interfere with anything else. A planet, crossing from beyond Mars to inside Mercury, sweeps through the entire inner system twice per orbit. Anything else that had formed on a stable orbit in that region would have been scattered out or absorbed long ago. Whatever else this system once contained between the star and 2.5 astronomical units is no longer there, and the planet's path is the reason. In 2016, Kane and colleagues published a result in the Astrophysical Journal that is unusual for a planet found by radial velocity. They detected evidence of reflected light, a flash of starlight bouncing off the planet as it swung through closest approach. That measurement is only possible because of the eccentricity. A planet's reflected brightness depends on how much light is falling on it and on the phase angle at which we see it, and for most planets on most orbits, both quantities change slowly and the signal stays buried. Here, both spike together for a few days, and the total brightness of the system rises by an amount that careful photometry can detect. It is one of very few reflected light detections for a non-transiting planet found by radial velocity, and it puts real constraints on the atmosphere. Kane's own eccentricity value in that work is 0.956, slightly lower than O'Toole's. The record stands either way. What nobody can explain is why the orbit is like this. Planets do not form on cometary paths. They condense out of a flat disk on near-circular orbits, and something has to happen afterwards to throw them onto a trajectory like this one. The usual suspects are gravitational scattering by another giant planet, or a distant stellar companion driving a long-period oscillation. No second massive planet has been found in this system to blame. And the star is 8.5 billion years old, which means whatever happened here happened a very long time ago and has left no other trace. The word record deserves a small caveat. It is a record among measured orbits, and measurement is biased. Radial velocity is best at finding planets whose signals are large and repeating, and an extremely eccentric orbit produces a signal that is nearly flat for most of the period and then spikes. If the observations do not happen to cover the spike, the planet is invisible. There may well be worlds on stranger paths than this one, sitting in systems that have been observed for years without anyone noticing anything at all. Every planet in our own solar system moves on a near circle. For most of human history, that was assumed to be how planetary systems simply are. It is only by looking outward that we learned near circles are a preference, not a rule. The next world does the same thing on a scale nobody alive will see completed. Number 8. The planet that took 20 years to catch. In August of 2019, Sarah Blunt published a paper in the Astronomical Journal with a title that reads like a technical note: Radial Velocity Discovery of an Eccentric Jovian World Orbiting at 18 Astronomical Units. She was a graduate student at Caltech at the time, working with Andrew Howard, Michael Endel, Lauren Weiss, and William Cochrane. The star is 102.7 light-years away in Virgo, and it is called HR 5183. The data behind that paper begins in the 1990s. That is the fact to hold on to through everything else in this item. The discovery rests on more than 2 decades of radial velocity measurements of a single star, gathered across several telescopes including Keck's Hires spectrograph and instruments at McDonald Observatory in Texas. Different people, different nights, different decades, the same star, over and over, with no guarantee that anything would ever come of it. The planet's mass is 3.31 Jupiter masses. Its eccentricity is about 0.87. And the path it travels is the reason it is here. From 2.87 astronomical units at closest approach out to 41.8 astronomical units at its farthest. In our terms, that is from inside Jupiter's orbit to well past Neptune's, on a single loop. It is worth putting the outer distance into a frame. 41.8 astronomical units is beyond Neptune and inside the region our own system reserves for ice, the inner Kuiper belt, where Pluto sits and where nothing large and warm has any business being. A 3-Jupiter mass planet spends the great majority of its long year out there in the cold, moving slowly, barely tugging on its star at all. Then it falls inward for years, accelerates, crosses the zone where an asteroid belt would be, passes closer to the star than Jupiter is to the Sun, and turns around. The period has never been directly measured. It is estimated at somewhere between 45 and 100 years, and the estimate is a range rather than a number because nobody has ever watched a full orbit. That is what makes the discovery unusual, and it deserves explaining properly because it is not how planets are normally found. Ordinarily, a radial velocity detection looks like a wave. The star's velocity rises and falls in a regular pattern. The pattern repeats, and you fit a curve through several cycles. Repetition is what convinces you. It rules out a one-off instrumental problem, it rules out a star spot, and it pins the period tightly because you can count the cycles. Blunt's team did not have a wave. They had one peak. Over 20 years, the star's velocity drifted slowly, then climbed, then reached a maximum, then fell away again, a single hump in a 2-decade baseline. That hump is the planet swinging through its closest approach, moving fastest, tugging hardest, and then receding. Everything else about the orbit had to be reconstructed from the shape of that one event. Andrew Howard described the motion this way. The planet loiters in the outer part of its star's planetary system, then starts to accelerate inward and does a slingshot around its star. The press picked it up as the whiplash planet. There is a real constraint on this kind of detection, and it should be said, it only works if the observing baseline happens to bracket the moment of closest approach. Had the program started 30 years later, the same star would have shown a slow, featureless drift, and nothing more. The planet was not found because the technique is powerful. It was found because a group of people kept measuring one star for 20 years, and the planet happened to come round while they were watching. There is a second reason this kind of detection is rare, and it has to do with instruments rather than patience. Radial velocity measurements taken 30 years apart have to be placed on the same scale, and the spectrographs involved were not the same spectrographs. Each instrument has its own zero point, its own systematic drifts, its own history of upgrades that shift the calibration. Combining decades of data from several telescopes into one coherent velocity curve is a substantial piece of work in itself, and it is the sort of work that produces no headline and appears in a paper as a single sentence about offsets being fitted as free parameters. The cause of the eccentricity is not known. The leading hypothesis is a violent gravitational encounter with another giant planet, one that was subsequently thrown out of the system altogether. That is a scenario built from dynamics rather than something anyone has observed. If it is right, then somewhere in that neighborhood there is now a rogue planet moving between the stars, unobservable and permanently anonymous, and the only evidence it ever existed is the shape of the orbit it left behind. Stephen Kane and Sarah Blunt examined what could still survive in a system like that in a 2019 paper with the honest title "In the Presence of a Wrecking Ball." Further dynamical modeling followed in 2021. The short version is that a planet crossing from inside Jupiter's orbit to past Neptune's every few decades does not leave much room for anything else. One more measurement closed a loop that radial velocity normally leaves open. A radial velocity detection only gives a minimum mass because the technique measures motion along our line of sight, and if the orbit is tilted, the true mass could be far higher. In 2022, Venner, Pierce and Vanderberg published work in monthly notices using astrometry, the star's tiny side-to-side motion on the sky rather than its motion toward and away from us, and showed the orbit is close to edge-on. That means the minimum mass is very nearly the real mass. 3.31 Jupiter masses is not a lower bound. It is the answer. The number 18 in the paper's title is the semi-major axis, which is the average of the closest and farthest distances rather than either of them. It is a useful reminder that a single number describing an orbit can conceal almost everything interesting about it. 18 astronomical units sounds like a cold, distant, unremarkable giant planet. The actual path swings by a factor of 14 in distance and a factor of 200 in the starlight received. There is one more thing worth noting about a planet on a path like this. Everything we can say about it comes from a single closest approach, which means the orbit as published is a best fit rather than a traced path. If the period is nearer 45 years, the planet is doing something quite different from what it would be doing if the period is nearer 100. Both remain consistent with the data. The object is confirmed, its mass is now well determined, and one of the two numbers that define its journey is still a range. Now, the part of this item that is not about physics. Nobody who made those measurements will live to see the orbit close. That is not a figure of speech, and it is not sentiment. It is arithmetic. The period is somewhere between 45 and 100 years. The next closest approach is decades away. Confirming the period, the single most basic fact about any orbit, the thing you would want first, will fall to people who are not yet working in the field, using instruments that have not been built, analyzing a dataset that will by then have 3 names on it that nobody in 2019 had heard of. And the measurements were made anyway. Night after night, for 20 years, on a star that showed nothing interesting for most of that time, by people who could not have known whether anything would come of it. That is the ordinary condition of this work, and it is almost never mentioned. Most of what is on this list exists because somebody kept a program running past the point where it was obviously worth it. The next worlds were already ancient when the sun was formed. Number 7. 5 worlds older than almost everything. On the 27th of January 2015, Tiago Campante and colleagues published a paper in the Astrophysical Journal titled "An Ancient Extrasolar System with 5 sub-Earth-size planets." Teams at Birmingham and at McDonald Observatory were central to the work. The system lies 117 light-years away in Lyra, and it is called Kepler 444. The detection combined 2 methods. Kepler supplied the transits, which give the planet's sizes relative to the star. Asteroseismology supplied the star, and that is the part that made the result matter. Asteroseismology means listening to a star ring. Stars are not silent balls of gas. They oscillate, driven by convection in their outer layers, and those oscillations show up as tiny periodic brightness variations. The frequencies of those oscillations depend on the star's internal structure, and the internal structure depends on its mass, its radius, and how far through its life it has traveled. If you can measure the frequencies precisely enough, you can read the star's age directly, rather than inferring it from models of what a star of that color ought to be doing. It is worth appreciating why that matters. For most stars, age is the least well-known of all the basic properties. Mass can be estimated from brightness and color, radius from mass, temperature from a spectrum. Age has to be inferred by working out where a star sits on a theoretical track, and those tracks depend on assumptions about convection, rotation, and composition that are themselves uncertain. Ages quoted for ordinary stars can easily be wrong by 50%. Astroseismology sidesteps that whole chain. The oscillation frequencies are set by the star's actual interior, so what comes back is a measurement rather than a placement on a model. Kepler was the instrument that made this possible, and not because it was designed to. It was built to find planets by watching for transits, which requires photometry of extreme precision and long, uninterrupted stares at the same field. Those two requirements happen to be exactly what astroseismology needs. A mission built to catch shadows turned out to be an excellent instrument for listening. For Kepler 444, the age came out at 11.2 billion years, plus or minus 1. The universe is 13.8 billion years old. This system formed when the universe was less than 20% of its present age, roughly 2 billion years after the Big Bang. It is about 2.5 times the age of the Sun. It is the oldest known system of terrestrial-sized planets, and there is no close second. There are 5 of them, and every one is smaller than Earth. The radii, from innermost outward, are 0.403, 0.497, 0.530, 0.546, and 0.741 Earth radii. That is a smooth monotonic increase, each planet slightly larger than the one inside it, with no exceptions. In our own terms, the innermost is roughly Mercury-sized, and the outermost sits between Mars and Venus. 2 of the 5 are Mars mass. The innermost has a period of 3.6 days. All 5 orbit in under 10 days. The entire system, all 5 worlds, fits comfortably inside Mercury's orbit. The size ordering is not a coincidence and is worth a sentence. Compact multi-planet systems very often show this pattern, with the innermost planets smallest and each successive one slightly larger. The favored explanation is that the inner regions of a disk hold less solid material within reach of a forming planet, so the planets that assemble there run out of supply sooner. It is a pattern seen across the Kepler catalogue rather than a quirk of this system, which makes its appearance in an 11 billion-year-old system quietly significant. The process that built these worlds appears to have worked the same way then as it does now. Neighboring pairs sit just wide of first-order mean motion resonances, 5 to 4, 4 to 3, 5 to 4, 5 to 4. That phrase means the orbital periods of adjacent planets are close to simple whole number ratios, but slightly outside them, rather than exactly on them. That specific arrangement, near resonance but not in it, is a fingerprint of tidal evolution acting over an enormous span of time. The planets almost certainly did form in resonance, and then 11 billion years of tides pushed them fractionally apart. It is also a triple star system. Kepler 444a is orbited by a tight binary pair of M dwarfs, together called Kepler 444 BC, at about 66 astronomical units. Stand on the outermost of those 5 worlds, 11 billion years ago, and consider what the sky contains. The K-dwarf star is close and orange and large in the sky because the planet orbits in a matter of days. Off to one side, 2 red dwarfs move together as a pair, 66 astronomical units away, which is roughly twice Neptune's distance from the Sun. So they are bright points rather than disks, but they are unmistakable, and they are clearly 2 rather than 1. There is very little else. The galaxy is younger and smaller, and the sky above this world is missing most of the stars that would eventually fill it. And underfoot there is rock, which is the strange part, because at this point in cosmic history, the raw material for rock is barely there. The heavy elements, silicon, magnesium, iron, the ingredients of a terrestrial planet, have to be manufactured inside stars and then scattered by their deaths, and only a couple of generations of stars have lived and died so far. The galaxy has hardly begun making the stuff. And yet here are 5 finished worlds, orbiting in near resonance, already ancient by the standards of everything around them. The chemistry of the star confirms the picture the age implies. Galaxies will continue to drift. The stars overhead may appear eternal, but the great web of galaxies is always in motion. That is exactly what would be expected of something that condensed out of gas, which had been enriched by only a few generations of stars. For a long time it was assumed that stars this metal poor would struggle to form rocky planets at all, on the straightforward grounds that there was not much rock available. This system was one of the first clear demonstrations that the assumption was too strong. Whatever the minimum requirement for building small terrestrial worlds turns out to be, it was met a very long time ago. That is the weight of this item, and it is not about habitability. These planets are almost certainly airless and far too hot for anything at all. The significance is timing. Planet making did not wait. It did not require a chemically mature galaxy, or several generations of enrichment, or any of the conditions that intuition suggests. It began almost immediately, in whatever material was available, and then it ran continuously for 11 billion years while nothing anywhere was capable of noticing. Kepler 444's planets were finished and orbiting more than 6 billion years before the Sun existed. They have completed something in the order of 1 trillion laps around their star since then. Every one of those laps happened. None of them was observed by anything until a space telescope in Earth orbit read the star's oscillations in 2015. Now the problem, because this system had one, and it took 8 years to resolve. The binary pair is the difficulty. Earlier orbital solutions put Kepler 444 BC on a path that brought it inward to within about 5 astronomical units of the primary star. A stellar companion passing that close does something specific to a protoplanetary disk. It truncates it. It gravitationally strips the outer disk away and leaves only a small inner remnant. The calculations put the surviving material at roughly 4 Earth masses of dust. 4 Earth masses is not enough to build 5 planets, even 5 small ones, once you account for the enormous inefficiency of the assembly process. On its own numbers, this system should not have been able to form. That is an uncomfortable position, a set of planets that plainly exist, orbiting a star whose history says they could not have been made. Zhang and colleagues resolved it in the Astronomical Journal in 2023, in work from the McDonald Accelerating Stars survey. They used the Hobby Eberly telescope's high-resolution spectrograph, together with Keck Hires and Keck NIRC2 astrometry, to pin down the binary's actual orbit rather than the previously assumed one. The revised closest approach is 23 astronomical units, not 5. That single correction changes everything downstream. A companion passing at 23 astronomical units truncates the disk at about 8 astronomical units instead of very close in, and a disk of that size holds roughly 500 Earth masses of dust. 500 against 4. That is not a refinement. It is the difference between a system that cannot exist and one that is entirely unremarkable, and it arrived not from a new theory, but from measuring an orbit properly. There is a general lesson in that which will matter again before this list ends. The planets were never in doubt. The transits were real from the start. What was wrong was a number describing something else in the system, and the wrong number made the planets impossible. Fixing it required a decade, 3 telescopes, and a team willing to remeasure something everyone had already accepted. Rocky planets were being assembled 2 billion years after the Big Bang. The universe was building worlds long before it built anything that could ask about them. The next world is nearly as old, and it is made of a chemistry the galaxy had barely finished inventing. Number 6. Built from a galaxy that had barely made rock. In January of 2021, 2 teams announced the same system within days of each other. Lauren Weiss and colleagues published in the Astronomical Journal, working from the TESS-Keck survey using TESS transits and Keck-Hires velocities. Luca Laciadelli and colleagues published in monthly notices using TESS with HARPS North at the Telescopio Nazionale Galileo on La Palma. The star sits 275.6 light-years away and is catalogued as 2AY561. The star is the reason this item is here, and it is a different reason from the previous one. TOI 561 is a G9 dwarf at 5,372 Kelvin, about 0.8 solar masses and radii. Its age is 10 billion years, plus or minus 3. Its iron abundance is minus 0.41, which means it holds roughly 40% of the Sun's iron. And it is alpha-enhanced, meaning it is comparatively rich in oxygen, magnesium, and silicon relative to iron. That combination of chemistry, together with the way the star moves through the galaxy, identifies it as a member of the thick disk. The Milky Way has 2 overlapping disk populations. The thin disk is where the Sun lives, younger stars on nearly circular orbits, close to the plane, chemically enriched by billions of years of stellar deaths. The thick disk is older. Its stars formed before the galaxy settled into its present shape. They move on tilted and eccentric paths, and their chemistry records a time when supernovae of one particular kind, the massive, short-lived alpha element-producing kind, had done most of the enriching, and the slower kind that makes most of the iron had barely started. It is worth explaining what alpha enhancement actually records, because it is one of the few pieces of galactic archaeology that a single star can carry on its own. Massive stars live briefly and die as core collapse supernovae, and they produce a characteristic mix dominated by the so-called alpha elements: oxygen, neon, magnesium, silicon, calcium. Much of the iron in the galaxy, by contrast, comes from a different and slower channel, the thermonuclear detonation of white dwarfs, which requires a star to have first lived out its long life and then been disturbed. Those 2 clocks run at different speeds. Early in the galaxy's history, only the fast channel had contributed, so stars forming then are rich in alpha elements and poor in iron. A star with that signature is not merely old. It is old in a way that can be dated by chemistry alone. TOI 561 was the first system TESS confirmed as belonging to that old population, both chemically and kinematically. It is also the first ultra-short period planet known around such a star. The kinematic half of the identification is worth a line as well. Thick disk stars do not travel with the local flow. They move on orbits that carry them well above and below the galactic plane and that are noticeably out of round, so relative to the Sun, they appear to be moving quickly and in the wrong direction. Measuring that motion requires a precise distance and a precise proper motion, which is exactly what Gaia provides for hundreds of millions of stars. Chemistry says the star is old. Kinematics says it belongs to a population that formed before the disk settled. The two agree, and it is the agreement rather than either measurement alone that makes the classification solid. The planet's period is 0.45 days, which is about 11 hours, and its equilibrium temperature is near 2,300 Kelvin. Around a 10 billion-year-old star, an 11-hour year means the planet has completed something on the order of 8 trillion orbits. It is difficult to think of another number on this list that is quite so large and quite so uneventful. The density has been argued over in print, and the sequence is worth following because it shows how a number converges. Weiss's team got 3.24 Earth masses, plus or minus 0.83, at 1.45 Earth radii, which gives 5.6 grams per cubic centimeter, plus or minus 2.2. Lacadeli's team got 1.59 Earth masses, plus or minus 0.36, at 1.43 radii, which gives 3.0, plus or minus 0.8. Those two results do not overlap comfortably. Then in 2023, Brinkman and colleagues used Maroon X, a precision spectrograph on Gemini North built specifically to weigh small planets around cool stars, together with Hyers, and converged on 2.24 Earth masses, plus or minus 0.2, at 1.37 radii, 4.8 grams per cubic centimeter, plus or minus 0.5. Two independent teams arriving at incompatible masses from the same planet is not a scandal, and it is worth saying why. Radial velocity signals for planets this small are at the level of a meter or two per second, which is comparable to the motions of gas on the star's own surface. Different instruments have different systematics. Different teams make different choices about how to model stellar activity, and the answer depends on those choices. What eventually settles such a disagreement is almost never argument. It is a better instrument. Even at that converged value, it is the lowest density, ultra-short period super-Earth known. It is too light for an Earth-like mixture of rock and iron. That is the chemistry of its birth, showing through the planet's bulk properties. A galaxy poor in iron builds planets poor in iron, and a planet poor in iron has a smaller core and a lower density. The composition of a world orbiting a star 11 hours a lap, 275 light-years away, is carrying information about what the Milky Way was made of 10 billion years ago. The two teams also disagreed about how many planets there were, and that disagreement is instructive. Weiss read 2 transits appearing in Test Sector 8 as a single planet on a 16-day period, giving 3 transiting planets. Lacadeli read the same 2 events as single transits of 2 different planets, giving 4. Same light curve, same data, 2 readings. Cheop's follow-up settled it in Lacadeli's favor, 4 transiting planets, with D at 25.7 days and E at about 77. In 2025, JUST returned a NEA-spec dayside emission measurement from 3 to 5 microns, published in the Astrophysical Journal Letters. Bare rock was rejected at high significance. The dayside came out far cooler than the roughly 3,000 Kelvin expected for an airless world at that distance, which is evidence for a thick, volatile envelope, an atmosphere substantial enough to move heat around. That is a genuinely unexpected result. A planet with an 11-hour year, at 2,300 Kelvin, orbiting a 10-billion-year-old star, appears to have kept or rebuilt a significant atmosphere. Every erosion argument in this field says it should not have. This planet was assembled from material that existed before most of the iron in your blood was made. It is still there, and it may still have air. The next world we have actually photographed, and we still cannot say what it is. Number 5. The magenta world whose mass depends on a number nobody agrees on. From here to the end of this list, the barrier stops being physical. The remaining 5 worlds are not unreachable because they would destroy you, or because they are far, or because they are old. They are unreachable because we cannot say what they are. This one we have a picture of. Masayuki Kuzuhara and colleagues published it in the Astrophysical Journal on the 8th of August, 2013. The image was taken with the Subaru 8.2-meter telescope on Mauna Kea, using the high CIAO camera and the AO188 adaptive optics system as part of a 5-year survey called SEEDS that was built specifically to photograph young giant planets. The image itself was captured in 2011, and the companion was confirmed in 2012 by Common Proper Motion, the same test that established the pairing at number 10 on this list. Direct imaging is worth a moment, because it is the rarest of the detection methods and the most demanding. Almost every planet on this list was found indirectly, by watching a star dim or wobble. Photographing a planet means separating a faint point of light from a star that may be 1,000,000 times brighter, sitting a fraction of an arcsecond away. Adaptive optics does part of the work by deforming a mirror hundreds of times a second to cancel the blurring of Earth's atmosphere. Coronagraphs do the rest by physically blocking the starlight. Even then, the only objects within reach are young, warm, and far from their stars, which is a small and biased corner of the population. It was the first direct image of a planet around a sun-like G star, and the coldest imaged companion of the era before Juiced. The system is about 57 light-years away. The projected separation is 43.5 astronomical units, with a semi-major axis greater than 27.8. The effective temperature was originally measured at 510 Kelvin and has since been refined to 564 plus or minus 4. That is cool. Not cold. 564 Kelvin is about 290 degrees Celsius, but far cooler than almost anything else that has been directly imaged, because almost everything else that has been imaged is young and hot and still glowing fiercely from its formation. Its color is what gave it a reputation. Its near-infrared color index, J-H, is minus 0.23 magnitudes. That is a negative value, which means it is blue rather than red in the near-infrared, and for a cool object that is unusual. Most cool substellar objects develop condensate cloud decks that redden them substantially. A blue near-infrared color implies an atmosphere that is nearly free of clouds. Combine that with the deep methane absorption in its spectrum and the rendering that comes out, the one that has appeared on every article about this object, is magenta. Now the problem, and it is the reason this world is at number 5 rather than somewhere unremarkable. There is no dynamical mass measurement for GJ504b. Nobody has weighed it directly. Luminosity is the only observable, and luminosity alone cannot distinguish a young, low-mass object from an older, heavier one. Both are cooling. A small object that formed recently and a larger object that formed long ago and has had time to fade can produce exactly the same brightness. To break that degeneracy, you need the age of the system, and the age of this system has been fought over for a decade. Kuzuhara's team used gyrochronology and chromospheric activity. The star rotates once every 3.33 days, which is fast, and fast rotation normally means youth, because stars shed angular momentum steadily through their stellar winds and slow down as they age. That reasoning gave an age of 160 million years, which implies a companion mass of about 4 Jupiter masses. A giant planet. Furman and Cheney argued in 2015 for something much older and heavier. Then, in 2017, Valentina Dooradze and colleagues published a careful reassessment in astronomy and astrophysics. They ran a line-by-line differential abundance analysis against reference stars and found the surface gravity to be 0.2 decs lower than a main sequence star of that type should have. Lower surface gravity means a larger, more distended star, which means the star has left the main sequence and is past its turn-off. Their age is 1.8 to 3.5 billion years, which implies about 25 Jupiter masses. A brown dwarf. In 2018, Michael Bonnefoy and colleagues combined Cara interferometry, which measures the star's angular size directly, with SOFI spectroscopy and sphere imaging. They measured the stellar radius at 1.35 solar radii and got an answer that is genuinely bimodal, 21 million years, or 4 billion. The same luminosity maps to 1.3 Jupiter masses under the first and 23 Jupiter masses under the second. That is a factor of nearly 20 in mass for an object we have photographed. The difference between 4 Jupiter masses and 25 is not cosmetic, and it is worth being clear why. Below about 13 Jupiter masses, an object never fuses anything and is generally called a planet. Above it, deuterium fusion becomes possible early in life. But the deeper distinction is one of origin. Planets are thought to assemble from the material of a disk, piece by piece, while brown dwarfs form the way stars do, by the direct collapse of a cloud fragment. Those are two completely different histories. Deciding which one produced this object is not a labeling exercise. It is a question about what actually happened here. Joest appears to have decided it. Babaraj and colleagues published in 2026 using NIR spec at a resolving power around 2700 from 2.9 to 5.3 microns. They detected water, carbon monoxide, methane, carbon dioxide, ammonia, and hydrogen sulfide, along with 2 isotopologues, carbon-13 monoxide and carbon monoxide 18. Isotopologue detections in substellar atmospheres are rare and carry information about formation history. The retrieved mass is 25.2 Jupiter masses, matching evolutionary masses of 19 to 27 at ages of 2.5 to 4 billion years. That is brown dwarf territory. The metal enrichment at plus 0.67 tentatively supports a planet-like formation route even so, which leaves the object in an odd position, probably too massive to be called a planet, and possibly formed like one anyway. There is a separate line of evidence that explains the whole confusion. Work using Erosita X-ray data and a 2026 paper in Astronomy and Astrophysics argue that only one scenario accounts for both the star's fast rotation and its X-ray brightness at the same time. The star swallowed a close-in Jupiter 1 to 2 billion years ago. Engulfing a planet delivers angular momentum to the star and spins it up. So the star is genuinely old, and it looks young because it ate something. If that is right, then gyrochronology was not misapplied. It was applied to a star that had broken the assumption underneath it. We have a picture of this world, taken from 57 light-years away. We can list the molecules in its atmosphere, and we still cannot say with confidence whether it is a planet. The next world is the inside of a planet, sitting in the open. Number 4, the naked inside of a gas giant. There is a core at the center of Jupiter. nobody has ever seen it, and nobody ever will. It is buried under something like 300 Earth masses of hydrogen and helium, compressed to conditions no probe will survive, and the best estimates of its size come from measuring how Jupiter's gravitational field departs from that of a uniform sphere. Even those estimates disagree. Somewhere between 10 and 25 Earth masses of rock and iron and ice, sitting at the middle of the largest planet in our solar system, permanently out of view. 700 light-years away, something very like it is sitting in the open. David Armstrong of the University of Warwick and colleagues published 2I849b in Nature on the 1st of July 2020 from test transit photometry combined with HARPS radial velocities taken at ESO's La Silla Observatory in Chile. The title of the paper is exact and unadorned: A Remnant Planetary Core in the Hot Neptune Desert. The location of this planet is worth connecting back to something earlier on this list. TOI 849b sits in the same hot Neptune desert that made the world at number 14 remarkable, but it occupies it from the opposite direction. DNGTS-4b is a planet that kept an envelope it should have lost. This one is a planet that has already lost everything the desert is supposed to take. Between them, they bracket the entire question. One is the exception the mechanism cannot explain, and the other is the mechanism's expected product, sitting where the theory says the leftovers should be. The orbital period is 18.4 hours. The mass is 39.1 Earth masses. The radius is about 3.4 Earth radii. And the density that falls out of those two numbers is 5.2 grams per cubic centimeter, which is essentially Earth's density, on a body 40 times Earth's mass. That density is the entire story, and it needs unpacking, because bulk density is one of the few things about a distant planet that admits almost no interpretation. Mass comes from radial velocity. Radius comes from the transit depth. Neither requires a model of the atmosphere or an assumption about the star's activity. Divide one by the other, and you have the average density of the object, and the uncertainty here is under 3 Earth masses, so the number is solid. 5.2 grams per cubic centimeter at 39 Earth masses means there is almost no gas. Any hydrogen and helium envelope can amount to at most 3.9% of the total mass. For comparison, Jupiter is around 99% hydrogen and helium by mass. Neptune, which is far smaller, is still something like 10 to 20%. It is worth being clear that 18.4 hours is not merely a short year. At that period, the planet is skimming close enough that it passes through the outer reaches of the star's magnetic environment on every lap, and it has done so for however long it has been there. Whatever atmosphere remains is not sitting quietly. It is being pulled at continuously by a wind that never stops, on a body whose gravity, while substantial for a rocky object, is nothing like a gas giant's. And that is the problem, because standard core accretion theory says this object should not exist. The theory works like this. A planet grows by accumulating solids until its gravity is strong enough to hold onto gas from the surrounding disk. As it gathers gas, its gravity increases, so it gathers gas faster. Past a critical core mass, usually quoted somewhere in the range of 10 to 20 Earth masses, that feedback becomes runaway, and the object accretes an enormous envelope within a few 100,000 years, which is very fast by the standards of planet formation. 39 Earth masses is well beyond that threshold. So TOI 849b should be a Jupiter. It is instead, as far as anyone can tell, the core that a Jupiter would have been built around, with nothing on top of it. The discovery paper does not choose between explanations, and neither should anyone repeating it. There are three on the table. The first is thermal self-disruption, or Roche-Lobe overflow. If the envelope was heated enough to inflate substantially, the outer layers could have expanded past the point where the planet's own gravity held them more strongly than the stars, and the star would then have taken them. The second is a giant impact. A collision between two forming planets at the right speed and geometry can strip the gas from both while the dense cores survive and merge. That would make this object the merged remnant of a catastrophe. The third is the least dramatic and possibly the most likely. It never accreted much gas in the first place. A planet that opens a gap in the disk cuts itself off from its own supply. A planet that forms late, after the gas has dispersed, never has a supply at all. In either case, nothing has to be removed, because nothing was ever added. The three explanations also differ in what they imply about how common such objects should be. Self-disruption requires a particular thermal history. A giant impact requires a coincidence of timing and geometry, so it should be rare. Failing to accrete gas in the first place requires nothing unusual at all, and would predict that exposed cores are common and simply hard to find. Which explanation is right is therefore not only a question about one planet. It is a question about how many more of these are out there. Pezzotti and colleagues complicated the picture usefully in Astronomy and Astrophysics in 2021. They argued that the host star's rotational and X-ray history could have removed an entire envelope even from a Jupiter mass progenitor. That matters because photoevaporation, in the standard treatment, is not nearly powerful enough. It typically removes a few Earth masses of hydrogen and helium over billions of years, not 300. That inadequacy is precisely why the collision hypothesis looked attractive. But the calculation depends on how active the star was in its first few 100 million years, and stellar activity histories are not directly observable. They have to be inferred from populations, and inferred quantities are where the disagreement lives. The host is a late G dwarf at 5,329 Kelvin, with an iron abundance of plus 0.2. That last figure is a small irony worth noting. Metal-rich stars are statistically more likely to host gas giants, not less. Everything about this system says it should have made a Jupiter. There is one further consequence, and it is the one that would matter most if anyone could act on it. The density, while Earth-like, is still slightly too low for a body made purely of rock and iron. That points to water in the interior, alongside the rock and the metal. And because photoevaporation cannot strip much, whatever thin atmosphere remains should be enriched with volatiles vented out of the interior itself, which would make TOI 849b something no other object offers, a chance to sample the inside of a giant planet directly. Not to model it, not to infer it from gravitational moments, but to measure the composition of material that would ordinarily be sealed under 300 Earth masses of hydrogen forever. There is a broader point in this that applies to several items on this list. We have never seen the interior of any planet, including our own. Everything known about the Earth's core comes from how seismic waves bend on their way through it. Everything known about Jupiter's core comes from tiny departures in its gravity field, measured by a spacecraft in orbit around it. Interiors are always inferred. This object is the closest thing to an exception that has been found, and it is 700 light-years away. No dedicated atmospheric observation of this planet has been published. So the inside of a gas giant is sitting exposed 700 light-years away at 1800 Kelvin, going round its star 3 times a day. We know its mass to within 7%. We know its density, and we have 3 incompatible stories about how it came to be that way, and no way at all to go and look. The next world was the first anyone ever photographed, and it has never looked the way it should. Number 3. The first planet anyone ever photographed, and it should not look like that. On the 27th of April 2004, Gail Chauvin and colleagues took an image at the Very Large Telescope in Chile using the NACO adaptive optics camera, and there were 2 objects in it. One was known. The other was not. It took a year to be sure. 2 objects appearing close together in an image may be genuinely close together, or one may simply lie far behind the other along the same line of sight. The test, once again, is motion. Watch for a year, and if both objects have shifted by the same amount in the same direction, they are traveling together. In April of 2005, the European Southern Observatory published the confirmation under a headline that has not aged. Yes, it is the image of an exoplanet. It was the first time anyone had directly photographed a world outside our solar system, rather than inferring one. The image that circulated was a composite assembled from H, K, and L-band infrared data, and it is one of the most reproduced images in the history of the field. The Gaia distance is 64.5 parsecs, plus or minus 0.4, which is about 210 light-years. The figure of 230 that appears in older material is a pre-Gaia estimate. The angular separation between the 2 objects is 0.773 arcseconds, which at the corrected distance works out to about 50 astronomical units projected. The 55 that is often quoted came from the earlier, larger distance. The mass is 5 to 6 Jupiter masses, from Kevin Luhman and colleagues in 2023, derived from a measured luminosity fed through evolutionary models. The temperature was measured at 1600 Kelvin, plus or minus 100, by Mohanty in 2007. Cloudless model fits give about 1300 against an expected 1200. No reliable orbital period has ever been published, which for an object at 50 astronomical units around a very low-mass host means centuries at minimum. The TW Hydrae Association is worth naming properly, because it is why this image exists, rather than some other. It is one of the nearest groups of young stars to the Sun, a loose collection of objects only around 10 million years old, drifting together through the local neighborhood. Youth is everything for direct imaging. A young companion is still hot from its own formation and therefore bright in the infrared. An old one of the same mass has cooled and become effectively invisible. Almost every early direct imaging result came from one of a handful of nearby young associations, and this one supplied the first. Now, the first strange thing. The host is not a star. 2M1207A is an M8 brown dwarf of about 25 Jupiter masses, a member of the TW Hydrae Association, 8 to 10 million years old. It never began hydrogen fusion. It is a failed star, glowing faintly with residual heat, and it has a companion of 5 to 6 Jupiter masses orbiting it at 50 astronomical units. That gives a mass ratio between companion and host of roughly 1 to 5. That ratio is the problem. In our own system, Jupiter is about 1,000th of the Sun's mass. Across the known population of planetary systems, the ratio of a planet's mass to its stars is typically in the thousandths or 10,000ths, because planets are built from a disk, and a disk contains only a small percentage of the star's mass. 1 to 5 is not a planetary ratio. It is far above the value in the IAU's working definition of a planet, and it is far above anything a circumstellar disk is expected to produce. The likely conclusion is that this pair formed the way a binary forms, 2 fragments of the same collapsing cloud condensing separately and staying bound, rather than the way planets form. The first exoplanet ever photographed may not have formed as a planet at all. Adaptive optics deserves a line as well, because without it, none of this happens. Earth's atmosphere is turbulent, and that turbulence smears a point of starlight into a blob many times larger than the telescope's theoretical resolution. Adaptive optics measures the distortion hundreds of times a second using a reference source, and then deforms a small mirror in the optical path to cancel it. The result is an image close to what the telescope could achieve in space. Two objects separated by 3/4 of an arcsecond are hopelessly blended without it and cleanly separated with it. Now the second strange thing, and it is the one that occupied the field for years. The companion is underluminous. It is about 2.5 magnitudes fainter than evolutionary models predict for its age and spectral type, which is a factor of 10 in brightness. That is not a small discrepancy. It is also very red in the near-infrared. And it is methane poor, despite being cool enough that methane ought to dominate its spectrum. Just finds the methane fundamental band absent altogether and carbon monoxide weak. The explanations arrived in sequence, and following the sequence is worth the time, because it is a good illustration of how a field converges on an answer without any single decisive observation. Mohanty and colleagues in 2007 proposed a disk of large grains seen nearly edge-on. Large grains produce extinction that is roughly the same at all wavelengths, so a disk like that would dim the object by a fixed amount without changing its colors much. It fits. Mamajek and Meyer, in the same year, proposed something else entirely, in a paper with the admirably honest title, An Improbable Solution. Their suggestion was that we were seeing the afterglow of a collision between protoplanets, an object that is genuinely hot and genuinely small at the same time, which resolves the tension by making the standard cooling tracks inapplicable. Skemmer and colleagues in 2011 found evidence against the edge-on disk. If the object was seen through a disk, small changes in the line of sight over time should produce brightness variability, and multi-epoch observations found none. They favored thick clouds instead. Barman and colleagues, also in 2011, put the pieces together. Clouds, plus non-equilibrium chemistry, plus low surface gravity, together reconcile the measured temperature with the cooling tracks without requiring anything improbable. Low gravity puffs the atmosphere out. Vertical mixing drives the chemistry away from equilibrium, which explains the missing methane, because carbon monoxide dredged up from below does not have time to convert. Galaxies will continue to drift. Clouds do the rest. The confirming argument came from elsewhere. HR 8799b, a directly imaged planet in an entirely different system, behaves the same way. Two independent objects showing the same anomaly points to atmospheric physics rather than a coincidence of viewing geometry, and that is the accepted resolution today. Just has since added a great deal. Luhmann and colleagues published the first 1 to 5 micron NIR spectrum in 2023 and found Paschen hydrogen emission and helium at 1.083 microns, accretion signatures, and the first evidence that the companion has a disk of its own. MIRI work in 2025 found hydrocarbon disk chemistry and silicate clouds and evidence for a circumplanetary disk. And a NAIRSpec time series in 2025 took 20 spectra over 12.5 hours, finding silicate and iron condensates with a variable cloud filling factor. That is weather measured directly on an object 210 light-years away. An object with its own disk raises a further possibility, which is that moons could be forming around a body that is itself orbiting a failed star. That is not a claim anyone has made from the data. It is simply what a circumplanetary disk is for, everywhere else it has been observed, and it is worth holding on to for a moment, because the last item on this list is about exactly that question asked in a different system. So the first world ever photographed turned out to be too faint for its age, orbiting something that never became a star, at a mass ratio no disk can produce, and probably not formed the way planets form at all. The next two worlds may be nothing more than the sound of a dying star ringing. Number 2. Two worlds that may only be a ripple in the starlight. Stéphane Charpinet and colleagues announced this system in Nature on the 21st of December 2011 under the title "A Compact System of Small Planets Around a Former Red Giant Star." It is about 4,015 light-years away. There was never a transit. That is the first thing to know, and everything else follows from it. What was measured instead is called orbital brightness modulation. The idea is that a close-in planet contributes to the total light of the system in two ways. It reflects some starlight, and it emits thermal radiation from its heated day side. As the planet goes round, the fraction of its lit face pointing at us changes, and so the combined brightness of star and planet rises and falls in step with the orbit. If you can measure that variation, you can infer the planet without ever seeing it cross the star. The variation measured here is roughly 50 parts per million. 50 parts per million is 5/1000ths of 1%. It is smaller than the transit depth of an Earth-sized planet crossing a sun-like star. It is, roughly, the difference between a lamp and the same lamp with a moth in front of it. That is the size of the signal from which two worlds were announced. The two candidate bodies have periods of 0.240104 days, which is 5 hours and 46 minutes, and 0.342887 days, which is 8 hours and 14 minutes. Their semi-major axes are 0.006 and 0.0076 astronomical units. Kepler 70b has a radius of 0.759 Earth radii and a mass of 0.440 Earth masses. Kepler 70c is 0.867 radii and 0.655 masses. It is worth being careful with those numbers because the figure 0.44 is widely misquoted as a radius. It is the mass. The host is where this becomes remarkable. Key IC 5807616 is a subdwarf B star, which is a stripped stellar core burning helium on what astronomers call the extreme horizontal branch. It has already been through the red giant phase. It expanded, it lost the great majority of its outer envelope, and what is left is the hot core, 0.496 solar masses packed into 0.203 solar radii at 27,730 Kelvin, with a mean density of 84.1 grams per cubic centimeter. It is worth pausing on what a subdwarf B star actually is, because it is the end state of a process our own sun will go through. A star of roughly a solar mass exhausts the hydrogen in its core, swells into a red giant, and at the peak of that expansion its surface may reach out past where Earth orbits today. Then it loses its envelope. Ordinarily, it retains enough to become a red clump star and then a white dwarf. A subdwarf B star is what results when the envelope loss is unusually severe. Nearly all of it goes, and the exposed helium-burning core is left behind, small and blue and extremely hot. Something drove that mass loss, and one of the standing questions in stellar astrophysics is what? Charpinet's framing was that these two bodies probably survived deep immersion inside the former red giant envelope. Possibly they are the evaporated cores of giant planets, and possibly their infall is what triggered the mass loss that stripped the star and created the subdwarf in the first place. If real, They are orbiting inside the volume the star's own surface used to occupy. That question is exactly why the claim attracted so much attention. If planets can be driven inward during the red giant phase and dumped into the star's envelope, they would deposit orbital energy in the outer layers and could plausibly help unbind them. A planetary explanation for subdwarf B formation would tie together two unrelated puzzles at once. It is an elegant idea, and elegance is not evidence. That is an extraordinary claim resting on a 50 parts per million signal, and the claim has been challenged twice, and the challenges have not been answered. Krasinski published in Astronomy and Astrophysics in 2015, working alone using Kepler quarters 5 through 17. His argument was based on asteroseismic mode identification. Subdwarf B stars pulsate, and their oscillation spectra are rich and complicated. In the low-frequency region where the planetary signals sit, the star has modes of its own. His title states the conclusion: planetary candidates around the pulsating subdwarf B star KIC 580716 considered doubtful. Then in 2019, Blokes, Krasinski, and Kedziora-Chudcha published a fuller analysis, and their wording is worth quoting directly. The two low-frequency Fourier transform signals found in KIC 580716, they wrote, are likely the combined frequencies of the lower amplitude pulsating modes of the star. Combination frequencies are a real and well-understood phenomenon in pulsating stars. When a star oscillates in several modes at once, non-linear effects in its atmosphere produce additional signals at the sums and differences of those frequencies. Those combination signals are genuine features of the data. They are just not planets. The same paper showed something else that should give anyone pause. The amplitudes of the low-frequency signals depend on how the data are extracted from the raw Kepler images. Different reduction choices give different amplitudes. Their recommendation was to raise the detection threshold for claims of this kind to 5 sigma. A number and a reduction are not the same thing. That sentence has already come up twice on this list, at number 18 where a weather report dissolved into supergranulation, and at number 13 where an atmosphere dissolved into a noise draw. Here it is again, and here it is not a property of a planet that is at stake. It is the planet. No published rebuttal from Charpinet or his co-authors has appeared. The dispute is effectively one-sided, which is not the same as settled, but it is not nothing either. And here is where the situation currently rests, and it is worth stating precisely. The NASA Exoplanet Archive lists both Kepler 70b and Kepler 70c as confirmed planets. It also carries an explicit controversial flag on both, with a note citing Blokes and colleagues in 2019. They have not been retracted. They have not been demoted. They are confirmed and flagged, and have been sitting in that condition for years. It is also worth flagging two figures that circulate widely about this system and do not appear in the Nature paper or the NASA archive: a dayside temperature near 7,000 Kelvin and a date of 18.4 million years since the star left the red giant stage. Both should be treated as unsourced. So, two worlds that may have survived being swallowed by a dying star, orbiting inside where its surface used to be, in under 6 and 8 hours respectively. Or two overtones of that star's own ringing, which leaves one world. The largest on this list, and the only one whose existence is still an open argument. Number 1, the largest world on this list, and it may not be there at all. Every world so far has been unreachable for a reason you could point at: heat, radiation, distance, time, an orbit that no engine could match. At number 1, the reason changes completely, and it is the only barrier on this list that no amount of engineering would ever address, because the problem is not getting there. The problem is that nobody can establish there is anything to get to. On the 3rd of October 2018, Alex Tichy, David Kipping and Alex Schmidt at Columbia University published in Science Advances the first serious candidate for a moon orbiting a planet around another star. It had been flagged the previous year by the hunt for exomoons with Kepler survey, and the follow-up observation was Hubble Wide Field Camera 3 slitless spectroscopy, taken across the 28th and 29th of October 2017 under program GEO 15149. 40 hours of Hubble time on a single transit. It is one of the largest allocations ever given to observing one planet cross one star. The star is a G-type at 5,586 Kelvin, slightly evolved, with a radius between 1.72 and 1.82 solar radii, an iron abundance of plus 0.23, and an age of 8.5 billion years. That is nearly twice the age of the Sun, which means whatever happened in that system happened long before the Sun existed. It lies 2,310 parsecs away, 7,535 light-years. The popular figure of 8,000 is a rounding. The planet, Kepler 1625b, has a period of 287.378949 days, and a semi-major axis of about 0.878 astronomical units. Hold that number for a moment. 0.878 astronomical units is very nearly Earth's distance from the Sun, around a star very nearly like the Sun. This planet is not in a strange place. It is in the most familiar place on this entire list. Its radius depends on which catalogue you use. 6.06 Earth radii from the pre-Gaia-Morton catalogue, or 11.83 Earth radii, 1.06 Jupiter radii from Berger's post-Gaia revision. There is no mass in the NASA archive. The photodynamical modeling suggests several Jupiter masses, and the candidate moon is described as similar to Neptune in both mass and radius, orbiting at about 40 planetary radii. A Neptune-sized moon is not a small thing. Neptune is 4 times Earth's width and 17 times its mass. The largest moon in our solar system is Ganymede, which is about 2/5 of Earth's width and 1/40 of Earth's mass. If this object is real, it would be the largest moon anywhere in the known universe by an enormous margin, orbiting a gas giant at Earth's distance from a Sun-like star, 7,500 light-years away. 40 planetary radii is worth converting, because it is the one number here that sets the scale of the system. If the planet is about 1 Jupiter radius across, 40 planetary radii puts the moon roughly 2.8 million kilometers out. Our own moon sits 384,000 kilometers from Earth. Ganymede orbits Jupiter at about 1 million. So this is a wide orbit, but not an absurd one, comparable in proportional terms to the outer regular satellites of the giant planets in our own system. It is worth noting that a figure of 1.4 million kilometers circulates in popular accounts and does not follow from the published separation. A moon that large also carries a formation problem of its own. Regular moons form in a disk around their planet, and a disk around a Jupiter contains nowhere near enough material to build a Neptune. If this object exists, it was almost certainly captured, a planet that formed elsewhere in the system and was later taken into orbit. Capture requires energy to be removed during the encounter, which requires either a third body or a gas-rich environment, and neither is guaranteed to have been available. So the candidate is difficult to explain even before anyone asks whether it is there. It appears nowhere on the NASA Exoplanet Archives page for this system. Now the argument, and there is no honest way to shorten it. It runs to 7 rounds, and it is still running. Round 1. Tichy and Kipping, 2018. The evidence is two things: a transit timing deviation, meaning the planet arrived at a time that a lone planet should not have, and a dip of roughly 500 parts per million in the light curve outside the planet's own transit. A moon would produce both. The authors state in their own paper that the inference is dominated by a single but highly precise Hubble epoch. Round 2. Heller, Rodenbeck, and Bruno, 2019, in Astronomy and Astrophysics. They reproduced a similar planet and moon solution and then argued that the statistics used to judge it were not trustworthy. The likelihood surface is not well behaved, and the model comparison criterion applied to it is unreliable as a result. Their verdict: not a secure exomoon detection. Round 3. Kreidberg, Luger, and Bedell, also 2019, in the Astrophysical Journal Letters. They performed an entirely independent reduction of the same Hubble data. Their planet-only fit gives a reduced chi-squared of 1.01, which is essentially a perfect fit, and adding a moon does not improve it at all. Their conclusion: written out, the lunar transit signal was likely an artifact of the data reduction. Round 4. Tichy, Kipping and colleagues, 2020, in a paper called Loose Ends. Their response is not that the other team made a mistake in principle, but that the disagreement lies in the reduction rather than the systematics model, and they give specifics. The rival reduction has a visit change flux offset about 900 parts per million larger. It has roughly twice the centroid variation. It has about 3.5 times the correlation between flux and centroid position. Those are the fingerprints of a reduction that has left more instrumental signal in the data, not less. Round 5. Kipping and colleagues, 2022, in Nature Astronomy. A survey of 70 cool giant planets, which produced a second candidate, Kepler 1708b. Round 6. Heller and Hipke, 7th of December, 2023, in Nature Astronomy. A nested sampling photodynamical reanalysis. Their finding is that the evidence for the moon comes almost entirely from the shallowness of one Hubble transit, and that the moon in the fit is doing something else entirely. It is compensating for stellar limb darkening that the model does not otherwise constrain. Limb darkening is the fact that a star's disk is dimmer at its edge than at its center, and it is a nuisance parameter in every transit fit ever performed. They also found the second candidate's signal corrupted by stellar activity. Their injection recovery false positive rates were 10.9% and 1.6%. Round 7. Kipping, Tichy and colleagues, 21st of May, 2025, a matters arising response in Nature Astronomy. Their argument is pointed. Heller and Hipke used the same Hubble light curve that Heller's own 2019 paper had used to recover the dip, and their fits missed the deeper likelihood maximum, with what the response describes as apparently unconverged posteriors, returning a best-fit moon the same radius as the planet, which is physically absurd. They add that the rival light curve carries about 20% higher noise and discards 11% of the usable data. Their closing sentence is the honest state of the field. Both candidates remain viable, but certainly demand further observations. It is worth being explicit about something in this exchange that is easy to miss. Every one of those 7 rounds was published under names, in journals, using data that anybody can download. Nobody is hiding a reduction. Nobody is refusing to share. The disagreement is not about honesty or competence. All 4 groups are excellent and all 4 are working carefully. It is about the fact that extracting a 500 parts per million signal from a space telescope requires dozens of decisions, and reasonable people make those decisions differently, and the differences are larger than the thing being measured. Picture those 40 hours. Hubble is in low Earth orbit, so it does not stare continuously. It observes for part of each 96-minute orbit, and then Earth gets in the way, and the target is reacquired on the far side. That is what a Hubble transit light curve actually is, a set of segments, stitched together, each one carrying its own small offsets as the instrument warms and cools going in and out of shadow. Over those 2 days in October 2017, the planet moved across the face of its star, and the counts came down, held, and came back up. And then, in the hours afterwards, the light did something small. 500 parts per million. A dip about half the depth of a decent camera's noise floor, spread across segments taken on either side of an Earth occultation, in data that also contains the instrument's own thermal breathing. 7 papers and 8 years have been spent on the question of whether that particular wobble belongs to a moon, to the star's limb, or to the telescope. Nobody has ever re-observed it. The orbital period is 287 days, so transit opportunities come slightly less often than once a year, and every one of them is a scheduling contest against every other astronomer alive. There is a coda that makes the whole thing sharper. In 2025, the Kipping Group published a just search for moons around a different planet, Kepler 167e. Across 12 analysis grids, 7 showed what the paper calls a strong exomoon detection. And the team's own conclusion was that the driver is a mid-transit event that is highly ambiguous with a star spot crossing, and that the system should be re-observed in October 2027. They talked themselves out of their own detection, in print, and told everyone when to check. That is the shape of this whole list, arriving at its end. Every world here was found and measured and put permanently out of reach. At number 20, the barrier was a surface made of vapor. By the middle, it was distance and time and orbits that no engine could match. Then it became identity, a world we have photographed and cannot classify, a core with 3 origin stories, a first image that may not be a planet at all. And here at the end, the barrier is the thinnest one imaginable and the most complete. Not 7,500 light-years. 500 parts per million, in 40 hours of data, that 4 teams of careful people cannot agree about. The instrument was already pointed at it. That was never the hard part. Somewhere out there, 7,500 light-years away, a gas giant is going round a sun-like star at very nearly the distance you are from your own. It takes 287 days. It has been doing it for 8.5 billion years, since long before this solar system existed, and it will go on doing it whether or not anyone ever settles what is orbiting alongside it. Sleep well, and good night.